Hello there, and welcome back to Science to Fall Asleep. Tonight, we are leaving Earth far behind. There will be no familiar continents beneath us, no oceans we recognize, no sunrise that looks quite right, and no ordinary world waiting somewhere ahead. Instead, we are going to drift quietly through the darkness between the stars, moving from one strange planet to another, discovering worlds so unusual that some of them seem almost impossible. Imagine yourself floating gently through an endless black ocean. There is no sound here, no wind, no traffic, no voices, only distant stars scattered across an enormous darkness that stretches farther than the mind can comfortably imagine. And somewhere out there, hidden among those stars, are planets. Thousands of them have already been discovered beyond our solar system, and scientists expect there are billions more in our galaxy alone. Some are enormous, some are tiny, some orbit their stars in only a matter of days. Some are so close to their stars that their surfaces may be hot enough to melt rock. Others may be frozen in permanent darkness. There are planets covered by oceans, planets wrapped in clouds, planets with gigantic storms, planets with strange atmospheres, planets that may have been torn apart by gravity, and planets that appear to wander through the galaxy without a star to call home. Tonight, we are going to imagine traveling through these worlds slowly. There is no need to memorize anything. You don't need to keep track of where we are. You don't even need to stay awake until the end. If your eyes are already becoming heavy, that's perfectly fine. Let the words simply pass through your thoughts like distant starlight. And while you listen, imagine that our journey begins far beyond the familiar planets of our own solar system. Earth becomes smaller behind us. The moon disappears. The sun becomes just another point of light. Mars fades into the darkness. Jupiter becomes a distant speck. And eventually, even our entire solar system becomes difficult to distinguish from the surrounding stars. We continue outward, quietly, slowly, until the first truly strange world appears. It is a planet known as 55 Cancri E, a world orbiting a star relatively close to us on the cosmic scale. From a distance, it might look like nothing more than a small glowing sphere. But its location tells us something extraordinary. This planet races around its star in less than a single Earth day. Imagine that. A year on this world is shorter than one day on Earth. While you might sleep through one night here, that planet could have completed an entire journey around its star. Its orbit is extremely close, and because of that proximity, the world experiences tremendous heat. Scientists have studied it as one of the most fascinating examples of a rocky exoplanet exposed to extreme conditions. For a moment, imagine approaching its night side. The planet hangs in front of us, enormous in the darkness. The star shines intensely on the opposite hemisphere. The atmosphere, if present and stable under those conditions, would exist in an environment unlike anything found naturally on Earth. The surface may be dominated by intense heat, while the planet's composition and atmosphere continue to raise questions. We don't need to land. We simply drift past. The strange world slowly disappears behind us, and the darkness opens again. Ahead is another star, and around that star is another planet. This one is famous for a very different reason. It is HD 189733b, a hot Jupiter located roughly 64 light-years away. At first glance, the planet seems beautiful. Its atmosphere appears deep blue. But this is not a peaceful blue world like Earth seen from space. Its blue appearance is associated with an atmosphere containing silicate particles, and under the violent conditions of this planet, scientists have proposed something remarkably strange. The winds may be extraordinarily fast. Particles may be carried through the atmosphere at tremendous speeds. And under such extreme atmospheric conditions, tiny glass-like particles could be swept sideways through the clouds. So imagine looking toward the horizon. There is no gentle ocean, no familiar breeze. Instead, a gigantic atmosphere moves around the planet with unimaginable force. The clouds rush across the sky. The temperature remains intensely hot. And far above the atmosphere, the parent star burns brightly. Yet from our distant viewpoint, the planet remains strangely beautiful. A dark blue sphere floating against blackness. We don't hear the winds. We don't feel the heat. We simply watch. And then we move on. Because the universe is full of planets that become stranger the longer we look. Some are strange because of their temperatures. Others because of their size. Some because of the stars they orbit. And some because their very existence challenges what we once thought planets were supposed to look like. Farther away, we encounter KLT-9b. This is one of the hottest known exoplanets. It belongs to a category called hot Jupiters, enormous gas-rich worlds orbiting extremely close to their stars. But KLT-9b takes that concept to an extreme. Its atmosphere is exposed to such enormous amounts of radiation that temperatures can reach thousands of degrees. The planet's day side can become hot enough for molecules that would normally remain stable to break apart. At those temperatures, the atmosphere behaves in ways that feel more like extreme physics than familiar planetary weather. Imagine the planet from above. There is no blue Earth-like atmosphere. Instead, the world glows beneath the intense radiation of its star. The upper atmosphere is battered continuously by stellar energy. The planet is so close to its star that the distinction between a planet and an extension of the stellar environment begins to feel strangely thin. And yet it remains a planet, a massive world circling a star, a world with gravity, a world with an atmosphere, a world that has existed for millions of years in a place where Earth-like life would have no chance. We drift away from it. The light fades, and another strange world emerges. This time, imagine a planet that appears to have been stretched and distorted by the gravity of its star. The world is WASP-12b. It is another hot Jupiter, but its story is particularly dramatic. This planet orbits extraordinarily close to its star. So close that its star's gravity can pull material away from the planet. Imagine watching from a safe distance. The planet is no longer a perfectly isolated sphere. Its atmosphere can be disturbed by the enormous gravitational relationship between the two worlds. Material can escape from the planet and form a trail. Slowly, over immense stretches of time, the planet can lose part of itself to its star. There is something strangely peaceful about imagining that process from far away. Nothing happens quickly to our eyes. The planet moves silently. The star shines. The surrounding space remains completely still. But beneath that silence, gravity is constantly working. Every second, every minute, every year, for millions of years. And eventually, even something as enormous as a planet can be changed. We let WASP-12b disappear behind us, and our journey continues. Ahead lies a world with an unusual name and an even more unusual appearance. WASP-17b. This planet is enormous, but remarkably low in density. It is often described as a highly inflated planet. Imagine a world larger than Jupiter in diameter, but with surprisingly little mass for its size. Its atmosphere can be extremely extended. Instead of imagining a compact ball like Earth, picture an enormous, soft-looking envelope of gas stretched through space. Its clouds may contain particles that scatter light in unusual ways. And because the planet is so close to its star, the atmosphere is heated to extreme temperatures. From a distance, it might look almost ghostly. A gigantic planet with an atmosphere extending far above the deeper layers. We pass slowly over its upper atmosphere. There is no ground beneath us. No place to stand. Only clouds, gas, pressure, and darkness. The deeper we travel into such a planet, the greater the pressure becomes. Eventually, the familiar distinction between atmosphere and interior becomes difficult to imagine. There may be no solid surface waiting below, only layers becoming denser and hotter as we descend. So we remain above the clouds. And after a while, we turn away. The planet becomes smaller, then smaller still, until it becomes another faint point of light. The darkness feels larger now, and somewhere beyond it waits one of the most fascinating categories of planets discovered by astronomers. Worlds that may be unlike anything in our solar system. One such planet is TOI 700d. Unlike the extreme hot worlds we have just visited, this planet is interesting because it lies within the habitable zone of its star. That doesn't mean scientists know that it has life. It doesn't mean we know that it has oceans. It simply means that, under certain atmospheric conditions, temperatures could potentially allow liquid water to exist on its surface. And that possibility makes the planet feel strangely important. Imagine approaching it. The star is smaller and cooler than our sun. The planet moves quietly through its orbit. Perhaps there are clouds. Perhaps there are oceans. Perhaps continents. We don't know. And that uncertainty is part of the mystery. The planet could be completely barren. It could be covered in ice. It could have an atmosphere unlike Earth's. Or perhaps, under the right conditions, it could have environments where chemistry becomes unexpectedly complex. From our distant viewpoint, we cannot know. We can only observe the tiny amount of light passing between the planet and its star. And from that faint signal, scientists try to reconstruct an entire world. Think about how remarkable that is. A planet dozens or hundreds of light years away, invisible to the naked eye. Yet by studying a tiny dip in the brightness of its star, astronomers can discover that the planet exists. They can estimate its size, its orbit, sometimes its atmosphere, sometimes even clues about what that atmosphere might contain. The universe reveals its secrets through tiny changes in light. And those tiny changes can tell us about enormous worlds. We drift onward. Another planet appears. This one is Kepler 16b. And immediately, the view becomes familiar in a strange way. There are two stars, two suns. The planet orbits both of them. For anyone who grew up watching science fiction, the image might feel almost too familiar. A planet with two suns sounds like something invented for a movie. But Kepler 16b is real. It is a circumbinary planet, meaning it travels around a pair of stars. Imagine standing on its surface, assuming there were a surface suitable for standing. Two stars would move across the sky. Their positions would change. Their brightness would vary. Their shadows would behave differently from the single-star environment we know on Earth. The planet itself is a gas giant, so there would be no ordinary solid landscape beneath your feet. But if we could somehow watch its skies, the celestial choreography would be extraordinary. Two stars, one planet, one orbit, three objects locked together through gravity. The stars circle their common center of mass, while the planet moves around them both. And yet the system can remain stable. The universe does not need a single sun. It can build planetary systems around pairs of stars. We continue deeper into the night. And now another strange world approaches. Kepler 7b is a hot Jupiter with an atmosphere that has been studied using reflected light. Its clouds are particularly interesting. Scientists have found evidence that its atmosphere is not uniform. Different regions can reflect different amounts of light. Imagine looking down from orbit. Instead of a perfectly smooth sphere, you might see broad atmospheric patterns. Clouds, haze, bright regions, dark regions, all slowly changing as the planet rotates and travels around its star. There is something soothing about watching planetary weather from far away. Storms that might be enormous enough to dwarf continents move slowly across worlds where no human has ever stood. On Earth, weather can feel immediate. A cloud passes over your home. Rain falls. The wind changes. But from orbit, weather becomes a pattern, a moving texture across a spherical world. And from a distant star system, an entire planet can become nothing more than a shifting brightness in a telescope. We move onward. Far away, another planet waits. Kepler 10b was among the early rocky exoplanets discovered by the Kepler mission. It is much smaller than the gas giants we have encountered, and it is extremely close to its star. Its surface is believed to be intensely hot. Imagine a rocky planet where the familiar solidity of Earth exists under completely different conditions. Mountains, rock, minerals, perhaps enormous areas of molten material. But no cool oceans, no gentle atmosphere like ours. The star dominates the sky. The planet receives enormous amounts of energy. And yet, from a cosmic perspective, it remains a tiny world. A rocky sphere orbiting a distant star. When astronomers first began discovering planets around other stars, many wondered whether our solar system might be unusual. Perhaps planets were rare. Perhaps rocky worlds were rare. Perhaps systems like ours almost never formed. But then discoveries began arriving. And more discoveries. And more. The universe began to look less empty. Not because the darkness contained fewer stars than we thought, but because we were finally learning how to see the worlds hiding beside them. Now imagine the darkness around us filled with invisible planets. Worlds too distant to see. Worlds whose stars are too faint. Worlds whose orbits have not yet been detected. Worlds waiting for another generation of telescopes. Perhaps some of the strangest planets in the universe have not been discovered yet. We simply haven't learned how to find them. And that thought carries us deeper into the darkness. Ahead is Kepler 22b. This planet became famous because it was one of the early discoveries of a potentially habitable zone planet. It is larger than Earth. Its exact nature remains uncertain. It could be a world with a thick atmosphere. It could have oceans. It could have an environment completely unlike ours. The word habitable can sometimes sound more certain than it really is. But astronomers use it carefully. A habitable zone is simply a region around a star where conditions could potentially allow liquid water on a planet's surface. It doesn't guarantee life. It doesn't guarantee oceans. It doesn't guarantee comfortable temperatures. It only tells us that the distance from the star might allow the right conditions under the right atmospheric circumstances. And that small distinction matters. Because the universe is filled with planets that remind us how little a location alone can tell us. A planet can sit in a promising orbit and still be frozen. Or scorching. Or covered in a crushing atmosphere. Or lacking an atmosphere entirely. Kepler 22b remains mysterious. And perhaps mystery is the most peaceful thing we can carry through this journey. We don't have to know everything. Sometimes it is enough to know that something exists, far away, quietly orbiting its star, unseen by human eyes. We leave it behind. The stars continue to pass. And now we encounter one of the most famous strange worlds in modern exoplanet science. TRAPPIST-1e. The TRAPPIST-1 system is extraordinary because several Earth-sized planets orbit a small, cool star. The planets are packed relatively close together. From one world, Another planet could potentially appear much larger in the sky than the moon appears from Earth. Imagine looking upward. Instead of seeing one familiar moon, you might see another planet hanging in the darkness. Perhaps you could distinguish its illuminated hemisphere. Perhaps you could watch it move across the sky. And beyond it, another world. And another. The system is a remarkable example of how different planetary architecture can be from our own solar system. Our planets are separated by enormous distances. In TRAPPIST-1, several planets occupy compact orbits close to their small host star. The system feels almost like a miniature cosmic neighborhood. And among those worlds, TRAPPIST-1 has attracted particular interest because of its size and orbit. It receives an amount of stellar energy that makes it an intriguing candidate for further atmospheric study. But again, we do not know whether it has life. We don't even know exactly what its surface is like. We observe, we measure, we wait, and we imagine. The planet turns beneath us. The small red star glows nearby, and other planets move silently through the same system. For a moment, our journey pauses. Imagine the view from that system. 7 known worlds around one small star. A family of planets circling together in the darkness. Some may be rocky. Some may have very different atmospheres. Some may be too hot. Some may be too cold. And one or more may possess conditions that deserve even closer attention. But even this extraordinary system is only one among countless planetary systems scattered across the Milky Way. The galaxy stretches for roughly 100,000 light-years. And within that enormous structure are hundreds of billions of stars. Many of those stars have planets. Some systems may contain one world. Others may contain several. Some planets may have moons. Some may have rings. Some may orbit 2 stars. Some may have no star at all. And every planet is another experiment performed by nature. Different materials, different temperatures, different gravity, different radiation, different histories, different futures. We continue. The next world is WASP 76b, a planet famous for its extreme environment. This hot Jupiter orbits incredibly close to its star. One of the most fascinating ideas associated with this world involves iron. On the scorching day side, temperatures may become high enough for iron to vaporize. The planet is believed to be tidally locked, meaning the same side continually faces its star. So imagine one hemisphere trapped beneath perpetual stellar heat. The rock and metals in the atmosphere experience extraordinary temperatures. Farther around the planet, the night side is much cooler. And as atmospheric material moves from one side toward the other, conditions can change dramatically. Scientists have proposed that iron vapor could condense on the cooler night side and potentially fall as iron rain. Think about that quietly. A world where the sky might contain vaporized metal. A world where the difference between day and night is so extreme that material can evaporate on one hemisphere and condense on the other. No thunder, no sound, just chemistry and physics unfolding over an alien world. We drift over the boundary between day and night. The glowing hemisphere slowly fades behind us. The darker hemisphere comes into view, and the planet continues its silent orbit. Another world waits beyond it. WASP 121b. This planet is also extremely hot, and its atmosphere has been studied in remarkable detail. It is so close to its star that the star's radiation dramatically influences its atmosphere. Some observations suggest that heavy elements can escape from the planet's upper atmosphere. Imagine an atmosphere slowly leaking into space. The planet is not necessarily disappearing quickly. Nothing about the process needs to happen on a human timescale. But over enormous periods, a planet's atmosphere can evolve. Stars can strip atmospheres. Radiation can alter chemistry. Gravity can pull material outward. A world can gradually transform. And that transformation is one of the great stories of planetary science. Planets are not static. They are not perfect spheres frozen in time. They change. Their atmospheres evolve. Their surfaces cool. Their interiors move. Their orbits shift. Their stars age. And eventually, entire planetary systems can become something completely different from what they were when they first formed. We continue through the darkness. Our next destination is a world known as GJ 1214b. It is a sub-Neptune or mini-Neptune-sized planet that has long fascinated scientists. Its atmosphere is difficult to observe clearly because thick clouds or haze can hide what lies beneath. Imagine approaching the planet. At first, there is almost nothing to see. Only a thick atmospheric envelope. Clouds upon clouds. Layers of haze. The deeper surface remains hidden. Perhaps beneath the clouds is a deep ocean. Perhaps a dense atmosphere. Perhaps something completely unexpected. This is one of the recurring mysteries of exoplanet science. A planet may be visible, but its surface can remain invisible. We can measure its size. We can study how it blocks starlight. We can analyze tiny changes in the spectrum of light. But the actual world beneath the clouds remains hidden. It reminds us of Earth before humans developed the ability to see beyond its atmosphere. For thousands of years, people could look toward the sky and wonder. Now we have telescopes powerful enough to examine worlds around distant stars. And yet many of those worlds still keep their secrets. The clouds remain closed. The planet rotates. The star shines. And we move onward. Farther away, a strange planet called 55 Cancri F circles its star. It is a much colder world than its famous sibling, 55 Cancri E. The same planetary system can contain worlds with dramatically different environments. This is another lesson hidden inside the darkness. A planetary system does not need to produce identical planets. One world may be hot and rocky. Another may be a gas giant. Another may orbit farther out and experience much colder conditions. Another may have rings. Another may have moons. The architecture of a planetary system can be wonderfully diverse. And the star at the center can be surrounded by a collection of worlds that seem almost unrelated. Yet all of them formed from the same original disk of material. Dust, gas, ice, rock, metal. Over millions of years, gravity gathers these ingredients. Small pieces collide. Larger bodies form. Planetesimals merge. Some worlds become enormous. Others remain small. Some migrate closer to their stars. Others are pushed outward. And eventually, a planetary system emerges. But the final arrangement can look completely different from what we might expect. Our own solar system is only one example. The universe has had billions of years to build countless alternatives. We travel onward. A faint orange star appears ahead. Near it is another remarkable world, Proxima Centauri b. This planet is particularly interesting because its host star, Proxima Centauri, is the closest known star to the Sun. That means this planet exists in our cosmic neighborhood, and yet nearby is still an enormous distance. Proxima Centauri is more than 4 light years away. Even traveling at the speed of light, which no spacecraft carrying humans can currently achieve, the journey would take more than 4 years. For us, it is unimaginably far. But compared with the rest of the galaxy, it is practically next door. Proxima Centauri b is roughly Earth-sized and orbits within the star's habitable zone. But there is an important complication. Its star is a red dwarf. Red dwarfs can be active and produce powerful stellar flares. That radiation could have major effects on a nearby planet's atmosphere. So again, We find ourselves looking at a world where the word habitable is only the beginning of the conversation. Perhaps it has an atmosphere that protects the surface. Perhaps its atmosphere was stripped away. Perhaps the planet has a very different climate from Earth. We don't yet know, and perhaps future observations will tell us more. For now, Proxima Centauri b remains a distant possibility, a small world around the nearest star. A reminder that even the closest planetary systems can remain mysterious. The planet disappears into the darkness, and we continue. Farther out, we encounter Gliese 486b. This is another rocky world orbiting a red dwarf star. It is much too hot to be considered an Earth-like paradise. Its proximity to its star creates intense temperatures. Yet the planet is valuable to astronomers because it is relatively nearby and potentially easier to study than many distant exoplanets. This is something strange about astronomy. Sometimes the most important planets are not necessarily the most exotic. They are the ones that are easiest to observe. A world can become a laboratory, a place where scientists test methods for studying atmospheres. A stepping stone toward understanding planets that are farther away. Every discovery teaches us how to make the next discovery. And slowly, the map of the galaxy becomes clearer. We leave Gliese 486b behind. The darkness stretches ahead. And now we encounter a planet with a remarkable density. K2-141b. This is an ultra-hot rocky planet so close to its star that scientists have modeled conditions involving a magma ocean. Imagine a world where part of the surface may be molten rock, where the atmosphere could interact directly with vaporized minerals, where a permanent dayside faces intense stellar radiation. If the planet is tidally locked, one hemisphere remains under constant illumination while the opposite hemisphere remains in darkness. On the hot side, rock can melt, minerals can vaporize, atmospheric winds may transport material. On the cold side, those materials could condense. It is almost like a planetary scale cycle of evaporation and precipitation. Except instead of water evaporating from an ocean and falling as rain, minerals themselves may participate in the cycle. A rain of rock, a sky containing vaporized minerals, a surface shaped by extreme heat, and all of it happening silently. We float above the planet. The molten region glows faintly beneath us. The horizon curves away. The star burns beyond the edge. And then we leave. The universe grows quieter, not because the planets have disappeared, but because they are everywhere. There are too many to visit individually, too many stars, too many worlds, too many possibilities. And somewhere in the darkness is another planet waiting, one that may be even stranger. One such world is Kepler 452b, sometimes described as a potentially rocky planet orbiting within the habitable zone of a star similar to our Sun. The comparison to Earth has made it famous. But it is important to remember that similarity does not mean sameness. The planet is larger than Earth. Its exact surface conditions remain uncertain. Its atmosphere is unknown. Whether it has oceans is unknown. Whether it has life is unknown. Yet the planet invites imagination. Imagine a distant world receiving sunlight from a star somewhat like ours. Perhaps clouds gather over an ocean. Perhaps enormous storms travel across continents. Perhaps the atmosphere is thick and hazy. Or perhaps the planet is completely barren. From here, we cannot tell. We simply see a world moving through space. And sometimes the most beautiful part of astronomy is the boundary between what we know and what we do not. We know the planet exists. We know its orbit. We know its approximate size. But beyond those measurements lies an enormous unknown. That unknown is where imagination begins. And as our journey continues, we will encounter many more worlds like this. Worlds that have names made of letters and numbers. Worlds whose stars are so distant that their light began traveling toward us before modern civilization existed. Worlds that may already be different from the way we see them, because we are always looking into the past. When we look at a planet 100 light years away, we are seeing light that left its star 100 years ago. The planet we observe today may have changed. Its atmosphere may be different. Its storms may have moved. Its star may have changed. And yet its ancient light is only now reaching our telescopes. The farther we travel through the universe, the farther we travel through time. And that is perhaps the strangest planet of all. A world we see is never exactly the world as it is now. It is a memory carried by light. We drift onward, and somewhere ahead, a giant planet begins to emerge from the darkness. Its name is HAT P7b, another hot Jupiter, another world orbiting extremely close to its star. But this planet has been studied for atmospheric changes that reveal just how dynamic these alien worlds can be. Clouds can shift. Weather patterns can change. The planet's atmosphere can redistribute heat. Even a world without oceans or continents can have weather. And perhaps that is one of the most comforting thoughts for tonight. Weather is not unique to Earth. The universe itself is full of moving atmospheres. Clouds forming and disappearing. Storms spinning. Heat traveling. Particles colliding. Winds moving through gases. Planets changing under the light of their stars. Somewhere out there, enormous storms have been moving for millions of years. We don't hear them, but they are there. And now, as our imaginary spacecraft drifts farther away, those storms become smaller. The planet becomes a point, then a faint point, then nothing visible at all. The darkness returns, and we continue toward another strange world. Because this journey is only beginning, the darkness returns. For a while, there is nothing ahead except stars. Tiny points of light scattered across the enormous blackness, some steady, some faint, some almost hidden. And as we drift between them, it is worth remembering that every one of those lights could be another story, another star, another planetary system, another collection of worlds moving silently through space. Perhaps some of those planets are small and rocky. Perhaps some are giants. Perhaps some are covered in clouds so thick that no telescope can see their surfaces. And perhaps somewhere among them is a planet that has never been imagined by anyone on Earth. But for now, another world slowly emerges from the darkness. This one is HAT P11b, a planet with a size somewhere between Neptune and Saturn. It belongs to a class of worlds sometimes called warm Neptunes. Unlike the enormous hot Jupiters we have been visiting, this planet is smaller, but its atmosphere is still fascinating. As we approach, the planet appears deep blue beneath a hazy atmosphere. Its star illuminates one side. The opposite side disappears into darkness. The atmosphere stretches far above the planet, and high-altitude clouds or haze may obscure deeper layers. From this distance, the planet looks peaceful, almost gentle, but beneath that appearance is a world governed by unfamiliar chemistry and powerful gravity. The pressure increases as we descend. The atmosphere becomes denser. The temperature changes. There is no ordinary surface waiting below us. Instead, the planet gradually transitions from upper atmosphere into deeper and deeper layers. The farther down we went, the more difficult it would become to describe the environment using anything familiar from Earth. And that is true for many planets. A planet doesn't need to look dramatic from space to be strange. Sometimes the strangest thing about a world is what happens beneath the clouds. A blue sphere may conceal a crushing atmosphere. A white planet may hide a deep ocean. A A dark world may contain enormous amounts of heat beneath its surface. A small planet may have an atmosphere extending much farther than expected. The universe rarely follows the simple rules our eyes would prefer. We move away from hat P11b. Its blue glow fades. Another star appears, and around it is a planet known as GJ 436b. This world is particularly interesting because scientists have observed signs that its atmosphere may be escaping into space. Imagine a planet with a vast, invisible tail. Not a tail made of rock or ice like a comet, but a stream of atmospheric material slowly being carried away by stellar radiation. The planet itself remains intact, but the atmosphere interacts with the star. Particles receive energy. Some move outward. Some escape the planet's gravitational grip. And slowly, the boundary between planet and space becomes less permanent. We can imagine the planet floating quietly against the black background. Nothing appears to be happening. There is no explosion, no dramatic collapse, no sudden destruction, just a slow process. A little material escaping, then a little more. Over millions or billions of years, those tiny changes can matter. This is one of the great themes of planetary science. Time. A planet can survive processes that would seem enormous to us because planetary evolution happens across timescales almost impossible to imagine. A mountain on Earth can seem permanent, but planets can build mountains, erode mountains, create oceans, lose oceans, gain atmospheres, lose atmospheres, freeze, melt, break apart, and sometimes disappear completely. We leave GJ 436b behind. The faint atmospheric tail becomes invisible, and the star disappears into the distance. Ahead, another world approaches. This one is GJ 3470b. It is a warm Neptune-sized planet with an atmosphere that has been studied carefully because it may be losing material to space. The planet orbits relatively close to its star. Its upper atmosphere is exposed to stellar radiation. And again, we see the delicate balance between gravity and energy. Gravity tries to hold the atmosphere close. Radiation tries to push material outward. The planet exists in the middle of that struggle. Imagine drifting above its upper atmosphere. There is no solid horizon, no mountain range, no ocean, only layers of gas gradually thinning until they become almost indistinguishable from the surrounding vacuum. At some altitude, there is no obvious boundary. The atmosphere simply becomes space. The transition is gradual and strangely beautiful, because even Earth has such a boundary. Our atmosphere does not end with a sharp wall. It becomes thinner and thinner. Molecules become more spread apart. Eventually, the planet gives way to space. GJ 3470b simply experiences this process under far more intense conditions. We drift onward, and soon we encounter another world that is almost the opposite. A planet that is not defined by a thick atmosphere, but by the possibility of a remarkably thin one. LHS 3844b is a rocky planet orbiting a small red star. It is extremely close to its star. The planet is likely tidally locked, meaning one hemisphere may permanently face the star while the other remains in darkness. Imagine the dividing line between day and night. One side is constantly illuminated. The other side remains permanently dark. Between them is a region where conditions change dramatically. If the planet has little atmosphere, heat may not move efficiently from one side to the other. The day side could become extremely hot. The night side could become extremely cold. The planet would exist as a world of two permanent faces, one facing the star, one facing the darkness. We float above the night side. The surface is almost completely black. There is no sunrise waiting, The star will never rise here. Instead, it remains forever below the horizon. Far away, beyond the curvature of the planet, the illuminated hemisphere glows under the star. It is a world divided by permanent light and permanent darkness. And yet the planet continues to orbit. Quietly, predictably, endlessly, we move toward its distant horizon. The surface disappears. The star comes into view. And we leave. Another planet appears. LHS 1140b. This world is particularly interesting because it is a rocky planet around a red dwarf star and has been considered a promising target for studying whether an atmosphere exists. The planet is larger than Earth. Its gravity would be stronger. Its star is smaller and cooler than the Sun. And the planet lies in a region where temperatures could potentially allow interesting atmospheric conditions. Again, the word potentially is important. A habitable zone is not a guarantee. The planet could be frozen. It could be covered in oceans. It could have a dense atmosphere. It could have almost no atmosphere at all. But unlike many distant worlds, planets such as LHS 1140b can be examined more closely because their stars are relatively nearby. Imagine the planet slowly turning. Perhaps enormous clouds gather over its surface. Perhaps the atmosphere is thick enough to spread heat around the planet. Perhaps the night side glows faintly beneath an aurora. Or perhaps it is silent and barren. We simply don't know. And for tonight, that uncertainty is enough. We don't need to solve the planet. We can simply watch it. A small world around a faint red star. A tiny point of light carrying an enormous question. We move onward. The next planet is K2-18b. This world has received enormous scientific attention because it is a sub-Neptune-sized planet orbiting within the habitable zone of its star. Its atmosphere has been studied using powerful space telescopes. Scientists have detected molecules in its atmosphere and continue to investigate what those signals mean. But the planet is difficult to imagine. It is larger than Earth, smaller than Neptune, and its environment may not resemble either. It could possess a thick hydrogen-rich atmosphere. It could have a deep ocean beneath that atmosphere. It could be a world where water exists under immense pressure. Or it could have a completely different composition. Imagine descending through its clouds. The upper atmosphere is dark. The pressure increases. Cloud layers pass above and below us. The planet becomes deeper. The familiar distinction between sky and ocean may disappear. If a deep ocean exists, it might not resemble Earth's oceans at all. The pressure could become enormous. The water could enter strange high-pressure phases of ice. Ice does not always have to mean cold. Under enormous pressure, water can form solid structures even at relatively high temperatures. So somewhere deep inside an alien planet, there may be materials behaving in ways that feel completely unfamiliar. A world can contain water without having blue oceans like Earth. A world can contain hydrogen without having breathable air. A world can be in the habitable zone without being habitable. The universe keeps forcing us to be precise with our words. We drift upward again. The planet's atmosphere fills our view. Then the curvature becomes visible. K2-18b shrinks behind us. And another world takes its place. TOI 1231b is a warm sub-Neptune orbiting a relatively nearby red dwarf. Its temperature is not as extreme as some of the worlds we have visited. Its atmosphere could contain clouds or haze. And because the planet is relatively close, scientists have considered it a useful target for atmospheric observations. Imagine watching this planet from far away. The world appears soft. A faint sphere surrounded by layers of gas. There is no obvious surface, no sharp boundary between planet and sky. It almost resembles a giant atmospheric cloud that has somehow become a planet. But gravity holds it together. The planet follows its orbit. Its star illuminates it. Its atmosphere responds to radiation. And the entire system moves through the galaxy. Even a quiet planet is moving at extraordinary speeds. The Earth is rotating. The Earth is orbiting the Sun. The Sun is orbiting the center of the Milky Way. The Milky Way itself is moving through the universe. And every planet we have visited is participating in this enormous cosmic motion. Nothing is truly still. Yet from our imaginary spacecraft, everything feels calm. That is one of the strange gifts of space. Motion can look like stillness. We continue. A distant world known as TOI 270d appears ahead. This planet is another sub-Neptune-sized world. It is close enough to its star that scientists can investigate its atmosphere. The planet's exact nature remains uncertain. It may have a thick atmosphere. It may contain water. It may experience conditions completely unlike those on Earth. And because it is larger than Earth, its gravity and atmospheric pressure could create environments that have no direct equivalent in our solar system. Imagine standing beneath its clouds. The sky would be enormous. The atmosphere would extend above you in layers. The star would appear different from our sun, perhaps smaller, perhaps redder, perhaps dimmer. Yet the planet would still receive energy. Clouds would move. Chemistry would happen. Heat would travel. And somewhere deep below, the planet's interior would slowly release the heat left over from its formation. Even billions of years after a planet forms, its birth is not completely forgotten. The heat of formation can remain trapped inside. Radioactive elements continue to decay. The interior moves. Rock flows slowly. Magnetic fields may be generated. A planet that appears motionless from space may be alive with geological activity beneath its surface. We leave TOI 270d. The star becomes smaller, and another strange world appears. TOI 849b. This planet is particularly unusual because it may represent something like the exposed core of a former giant planet. Imagine a gas giant. A massive world surrounded by enormous layers of hydrogen and helium. Now imagine its outer atmosphere being stripped away over immense stretches of time. What remains? Perhaps a dense planetary core. Something far heavier and stranger than an ordinary rocky planet. TOI 849b is one of the worlds that has inspired this kind of discussion. Its existence raises questions about planetary evolution. Could a giant planet lose most of its atmosphere? Could a planet migrate extremely close to its star and experience such intense radiation that its outer layers are gradually removed? Could we be looking at the remains of something that was once much larger? We cannot simply look at a planet and know its entire history. Planetary science is partly detective work. Scientists examine mass, radius, density, orbit, atmosphere, temperature. Then they build models. They ask what kinds of histories could produce the world we see today. Perhaps TOI 849b began as a giant. Perhaps it lost its envelope. Perhaps it formed in an unusual environment. The planet remains a clue, a cosmic fossil, a remnant of a story that began billions of years ago. We drift past its surface. The world is dark and dense beneath the light of its star. Then it disappears. The darkness returns. And now another planet appears. WASP 107b. This is one of the most fascinating low-density gas planets known. It is large, but its density is surprisingly low. Imagine a planet almost the size of a giant gas world, yet with an atmosphere that is remarkably extended and diffuse. From space, it might appear almost like a glowing cloud wrapped around a hidden core. Its atmosphere extends outward, its star shines through the upper layers. And because the planet is so inflated, it becomes easier for starlight to pass through its atmosphere during transits. That gives astronomers an opportunity to study the gases surrounding it. The planet is another reminder that size alone does not tell us what a planet is made of. Two planets can be similar in diameter and have very different masses. Two worlds can have similar masses and completely different atmospheres. And two planets can orbit similar stars while experiencing entirely different climates. The universe does not build planets from a single recipe. It changes the ingredients. It changes the temperature. It changes the pressure. It changes the time available. And it lets gravity do the rest. We continue. Ahead is another enormous world. HAT P67b is an unusually inflated planet, orbiting close to its star. Its atmosphere may extend far above its deeper layers. The planet is so large and diffuse that its density is extremely low. Imagine looking at it from a distance. The edges of the planet would appear soft. Its atmosphere would fade gradually into space. There would be no sharp line, just layers of gas becoming thinner and thinner. It almost looks less like a solid planet and more like a giant cosmic breath suspended around a small central body. And yet beneath all that gas is a gravitational center holding everything together. Gravity is one of the quietest forces in the universe. You cannot see it. You cannot hear it. But it shapes galaxies. It builds stars. It forms planets. It holds moons in orbit. It pulls atmospheres toward surfaces. And it can even tear planets apart. Every world we have visited is essentially a conversation between gravity and energy. Gravity pulls inward. Heat pushes outward. Radiation changes chemistry. Time changes everything. We float away from HAT P67b. The giant world becomes smaller. The star fades. And our journey continues. Now we approach WASP 39b. This planet is another hot Saturn-like world that has become extremely important in atmospheric science. Its atmosphere has been studied in detail, including evidence of water vapor and other molecules. Imagine looking at the planet through a telescope. You don't actually see its clouds directly. Instead, scientists analyze the light passing through the atmosphere as the planet crosses in front of its star. Different molecules absorb different wavelengths. Those missing wavelengths create patterns. Patterns become measurements. Measurements become chemical clues. And chemical clues become an atmospheric portrait. It is almost like identifying a person from a fingerprint, except the fingerprint belongs to an entire atmosphere located hundreds of light years away. WASP 39b reminds us that planets can be studied without ever being visited. No spacecraft needs to land. No probe needs to enter the atmosphere. Sometimes all we need is light. Light travels through the atmosphere. The atmosphere leaves a tiny signature, and that signature crosses space. Eventually, it reaches a telescope on Earth or an orbit around Earth. And from that tiny signal, we reconstruct a world. The planet itself continues silently orbiting its star. Clouds move. Molecules absorb light. The atmosphere expands and contracts. And billions of kilometers away, someone on Earth studies the pattern. We drift away. The planet becomes a distant dot. And the universe opens again. Ahead is another hot world. WASP 43b. This planet is particularly interesting because it is close to its star and likely experiences enormous differences between its permanent day side and night side. Imagine one hemisphere facing the star continuously. The day side receives constant radiation. The night side remains turned away. Heat must travel through the atmosphere. Winds can carry energy from one side toward the other. The result is a planet with an enormous atmospheric circulation system. A world can have weather even when one side never experiences night. Clouds can form, winds can accelerate, temperature patterns can stretch around the planet. And all of it happens on a world without seasons like Earth's. No spring, no summer, no autumn, no winter. Instead, the planet's climate is organized around permanent day and permanent night. We slowly cross above the night side. The planet is dark beneath us. The stars are visible, but beyond the horizon, the day side glows. The atmosphere carries heat across the planet, and the boundary between the two hemispheres becomes a permanent region of transition. We continue. The next world is WASP 18b. This planet is a massive hot Jupiter orbiting extremely close to its star. Its orbit is so short that it completes one revolution in less than a single Earth day. Imagine waking up every morning and discovering that your planet had already completed another year. A lifetime would contain an unimaginable number of planetary years. The planet receives intense radiation. Its atmosphere is extremely hot, and because of its close orbit, the star's gravity strongly influences the planet. The system is locked into an intimate gravitational relationship, a giant world racing around its star, the star illuminating one side, space remaining silent, and the planet repeating the same orbit again and again, for millions of years, for billions. The repetition itself becomes almost hypnotic. One orbit, then another, then another. A planet does not need to travel anywhere new to experience something extraordinary. Its entire existence can be the endless repetition of the same path around a star. We watch another orbit begin, and another, then we drift away. Far beyond the hot Jupiter systems, we encounter a different kind of world. Kepler 186f. This planet is famous because it was one of the first Earth-sized planets discovered in the habitable zone of another star. Its star is a red dwarf, much smaller and cooler than our Sun. The planet receives less energy than Earth does, and yet its orbit places it in a region where liquid water might potentially exist under suitable atmospheric conditions. Imagine approaching it slowly. The planet is not blazing. It does not glow with molten rock. There are no gigantic rings, no obvious storms. It simply hangs quietly in the darkness. And perhaps that makes it stranger, because a planet does not need to be violent to be extraordinary. Maybe it has oceans, maybe clouds, maybe ice, maybe mountains, maybe nothing at all. We cannot see enough detail to know. But the possibility of a world with Earth-like dimensions around another star has always carried a special fascination. For centuries, humans wondered whether Earth was unique. Now we know that planets are common. The question has changed. It is no longer simply whether other planets exist. The question is what those planets are like, and whether some of them might share environments where life could emerge. That question remains open. We leave Kepler 186f behind. The star becomes a distant point, and another world appears. Kepler 62f. This planet is another candidate for a potentially habitable environment. It orbits farther from its star than Earth does from the Sun, but its star is different from ours. The planet is larger than Earth. Its atmosphere could dramatically influence its temperature. A thick atmosphere can trap heat. A thin atmosphere can allow heat to escape. Clouds can reflect sunlight. Ice can increase reflectivity. Oceans can transport heat. A planet's climate is a complicated conversation between all these factors. So even when astronomers know a planet's orbit, they may still be unable to predict exactly what the surface looks like. Imagine the planet slowly rotating. Perhaps one hemisphere is covered in ocean. Perhaps huge ice sheets reach toward the equator. Perhaps clouds cover the entire world. Or perhaps it is a barren rocky planet. The telescope cannot simply zoom in and reveal the answer. The planet is too far away. So we infer, we model, we compare, we wait for better observations. And sometimes, a planet can remain mysterious for decades. That is the beauty of the journey. There is always another question waiting, another observation to make, another planet to understand. The darkness grows deeper, and now we encounter Kepler 69c. This world attracted attention because of its position relative to its star. But again, the details remind us that a habitable zone does not automatically produce an Earth twin. Kepler 69c is larger than Earth. Its atmosphere could be very different. Its climate could be hostile. Its surface conditions remain uncertain. From our perspective, the planet is just a distant sphere. But beneath that sphere is an entire planetary history. Its formation, its early atmosphere, its collisions, its internal heat, its relationship with its star, its possible moons, its changing chemistry. Every crater, mountain, cloud, and atmospheric molecule would be part of that history. A planet is not merely a place. It is a story written in matter. We move onward. And perhaps the strangest thing about the universe is that these stories are happening simultaneously. While one planet experiences permanent daylight, another freezes in darkness. While one world loses its atmosphere, another gains one. While one planet has oceans, another has lava. While one world is being torn apart by gravity, another is quietly forming new mountains. All of this is happening at once, across the galaxy, across billions of years, and we are only visiting a handful. We continue our slow journey. Another unusual planet comes into view. GJ 1132b. This rocky world orbits close to a small red dwarf star. It is hot, very hot. Yet scientists have been interested in whether the planet might possess or regenerate an atmosphere. Some rocky planets can lose atmospheres under intense stellar radiation, but geological processes might potentially contribute gases back into the atmosphere. Volcanic activity can release gases. The surface can interact with the atmosphere. The star can remove particles. A planet can exist in a constant cycle between gaining and losing its atmospheric envelope. Imagine looking down upon the surface. Dark volcanic terrain, glowing regions perhaps hidden beneath clouds. A faint atmosphere stretching above. The planet is small compared with a gas giant, but its story may be enormous. Because worlds like this help scientists understand how rocky planets evolve. They show us that atmospheres are not necessarily permanent. They can be created, destroyed, rebuilt, changed. And perhaps Earth itself has experienced many such transformations throughout its history. Our planet's atmosphere today is not the atmosphere Earth had billions of years ago. The composition changed. Oxygen became abundant much later. The climate changed. The oceans changed. The continents moved. The planet evolved. So when we look at an alien world, we are not looking at a finished product. We are looking at one moment in a much longer story. GJ 1132b continues its orbit. We leave it behind, and the stars move around us. The next world is K2-3d. This planet is another super-Earth or sub-Neptune-sized world orbiting a red dwarf. It exists in a system containing multiple planets. Imagine a small star with several worlds moving around it. Some closer, some farther, each receiving a different amount of energy, each developing its own atmosphere, each evolving independently. Planetary systems can be like families. The worlds share an origin, but their lives can become completely different. One may be hot, one may be cold, one may have a thick atmosphere, one may lose its atmosphere, one may have oceans, another may be covered in ice. And yet all began from the same cloud of material. We watch K2-3D orbit. The star remains small and red. The surrounding planets move silently. The system is compact, quiet, and unimaginably distant. Then we continue. The next world appears as a faint sphere against the stars. HD 97658b. This is a super-Earth-sized planet orbiting a nearby star. It is larger and more massive than Earth, but smaller than Neptune. Worlds in this size range are particularly interesting because our solar system does not contain a planet exactly like them. We have Earth and Venus on the rocky side, then Neptune and Uranus among the ice giants. But many other planetary systems contain intermediate-sized worlds, super-Earths, mini-Neptunes, planets that fall into categories we do not have a perfect local example for. That is one of the most important discoveries from exoplanet astronomy. Our solar system is not necessarily the standard template. It is one arrangement among many. And perhaps the most common type of planet in the galaxy is something that our own solar system does not contain at all. A world larger than Earth, but smaller than Neptune. A world with a thick atmosphere. A world that may contain oceans deeper than any on Earth. A world that could be rocky beneath a dense envelope of gas. The universe has no obligation to copy our neighborhood. We continue. Ahead is GJ667cc. This planet orbits within the habitable zone of a red dwarf in a complex stellar system. Imagine not one star, but multiple stars gravitationally connected. The planet orbits one of them. Other stars remain farther away. The sky would be more complicated than ours. Multiple suns could appear at different positions. Their brightness would change. Their colors could differ. And the planet itself would move through this multi-star environment. The system reminds us that planets do not always live under a single sun. Some orbit binaries. Some exist in systems with several stars. Some may even have complicated gravitational histories. The night sky of another planet could look nothing like ours. Instead of one bright moon and countless stars, perhaps several suns appear. Perhaps another planet dominates the sky. Perhaps rings create enormous shadows. Perhaps the star itself looks tiny and red. The universe has an almost endless supply of different skies. We drift onward. And now a very unusual world appears. Kepler 413b. This planet orbits a binary star system and has an unusually tilted orbit. Its orientation can produce dramatic changes in how much sunlight it receives. Imagine a planet whose orbital path is not neatly aligned with the equator of its stars. Its seasons could be irregular. The amount of sunlight reaching different regions could change in ways that feel strange compared with Earth. The stars themselves move around each other. The planet moves around them. And the planet's axis has its own orientation. 3 layers of motion interacting. Gravity creates a complicated dance. From far away, however, the system appears peaceful. 2 stars. 1 planet. Endless darkness. The stars circle. The planet follows. And time passes. We leave Kepler 413b behind. The binary stars become smaller. And another unusual planet approaches. Kepler 47b. This is one of the planets discovered orbiting 2 stars. A circumbinary planet. Its existence is a reminder that planetary systems can form even in environments where 2 stars are gravitationally connected. Imagine a world where 2 suns rise and set. Sometimes they might appear close together, sometimes farther apart. Their combined light would change across the sky. The shadows would have more than one source. And the orbital mechanics would be far more complicated than Earth's simple journey around the sun. Yet the planet remains stable. Gravity finds a pattern. The stars orbit each other. The planet orbits both, and the entire system travels through the galaxy. We continue through the darkness. Now, another circumbinary world appears. Kepler 1647b. This planet is a gas giant orbiting a pair of sun-like stars. It is much farther from its stars than some of the compact circumbinary worlds we have encountered. Imagine a massive planet traveling around two stars separated by millions of kilometers. The stars orbit one another. The planet follows a much larger path around them. The geometry is beautiful. Three bodies moving through space. Two close together, one farther away, and all connected by gravity. The planet itself may have moons. If it did, those moons would experience an even more complicated gravitational environment. A moon would orbit the planet. The planet would orbit the two stars. The two stars would orbit each other, and the entire system would move through the galaxy. It is almost like watching several clocks ticking at different speeds. Each motion creates another layer of time. We drift away. The binary stars become tiny. The planet disappears, and the darkness continues. Somewhere farther away is another planet with an extraordinary atmosphere. HAT P26b. This warm Neptune-sized world has been studied for the composition of its atmosphere. Its atmosphere appears to be relatively rich in heavier elements compared with hydrogen and helium. This is important because planetary atmospheres preserve clues about how planets formed. If an atmosphere contains certain elements in certain proportions, scientists can ask where the planet originated. Did it form close to its star? Farther away? Did it migrate inward? Did it accumulate gases from the surrounding disk? Did it experience collisions? Atmospheres can preserve evidence of planetary history. A planet's sky can be a fossil record. We approach HAT P26b. The atmosphere is soft and hazy. The deeper layers remain hidden. There is no ground beneath us. But within the gas are molecules that carry a story billions of years old. And perhaps one day, more precise measurements will allow scientists to read that story more clearly. We move away. Another world appears. HAT P32b. This is a highly inflated hot Jupiter. Its atmosphere extends unusually far from the planet. The planet orbits close to its star, receiving enormous amounts of energy. Its outer atmosphere may reach surprisingly high altitudes. From a distance, it looks enormous. But much of that apparent size comes from the extended gas surrounding the deeper planet. Imagine passing through the upper atmosphere. The gas becomes extremely thin. Particles are separated by vast distances. There is no clear surface. We could travel through layers for thousands of kilometers without finding anything that resembles solid ground. The planet is less like a ball with an atmosphere and more like an atmosphere wrapped around a dense central body. And that distinction matters. On Earth, the atmosphere is a thin layer compared with the planet's radius. On some exoplanets, the atmosphere can become a much larger fraction of the visible world. The planet's boundary becomes blurred. Where does the planet end? Where does space begin? There is no simple answer. We drift away, and the darkness swallows the planet. Another star, another orbit, another world. The journey continues. And as your breathing becomes slower, perhaps you can imagine the planets passing quietly around you, one after another, not as numbers, not as a list, but as distant worlds in a single continuous cosmic landscape. A molten world fades behind us. A frozen world appears ahead. A gas giant turns slowly. A dark rogue planet drifts without a star. A world with two suns crosses the darkness. An ocean planet disappears beneath clouds. A planet loses its atmosphere. Another gains one. A planet burns. Another freezes. And still the stars remain. Quiet, distant, patient. We move deeper into the universe, and there are still many strange worlds waiting in the darkness. The stars continue to drift past us. For a moment, the universe seems almost empty, but the emptiness is deceptive. Between those tiny points of light are worlds we cannot see with our eyes. Worlds circling stars so distant that their light has traveled for centuries before reaching us. And somewhere ahead, another planet begins to emerge. A faint silhouette, a pale atmosphere, a small star burning behind it. We approach slowly. This world is WASP 69b, a hot gas giant with an extraordinary feature, an extended stream of atmospheric material trailing behind it. Imagine a planet moving through space while its own atmosphere stretches behind like an enormous invisible comet tail. The planet is close to its star. The stellar radiation is intense. Its upper atmosphere can be heated and energized until particles escape the planet's gravity. Those particles are then carried away. From far away, the world may appear almost ordinary. A planet, a star, a quiet orbit. But behind the planet, material is being lost. A long trail follows the planet through space. It is a reminder that planets can have tails. Not all tails belong to comets. Some belong to worlds. The planet continues its journey. The tail follows, and the star remains fixed in the background. We pass through the outermost edge of the escaping atmosphere. There is almost nothing there, just scattered particles. Then even those particles disappear. WASP 69b becomes smaller behind us, and the darkness opens once more. Ahead, another strange planet waits. WASP 127b. This is an unusually low-density gas giant, so inflated that its atmosphere extends far above the deeper layers. Imagine a world larger than Earth by many times, but with a density so low that it almost seems fragile. Its atmosphere is enormous. The star illuminates the outer clouds. The planet's shape is defined partly by its extended gases. If we could somehow see it close enough, it might appear soft around the edges. Not soft in the physical sense, of course. The pressure would become enormous deeper inside. But from a distance, its outer atmosphere looks almost delicate. This is one of the strange contradictions of giant planets. They can be enormous and yet extremely low in density. They can have enormous atmospheres while lacking any solid surface. They can appear calm while containing pressures and temperatures that would destroy anything familiar from Earth. We float above the clouds. The atmosphere stretches beneath us. Somewhere deep below, pressure continues increasing. And below that, more pressure, and more. Eventually, gases become so compressed that their behavior changes completely. Hydrogen can enter exotic states. Matter can behave in ways impossible to experience naturally on Earth's surface. The planet becomes a laboratory of extreme physics. We slowly rise again. The clouds fill our view. Then the curvature of the world appears. The planet shrinks behind us. And we continue. Another planet approaches. WASP 79b. This world is a hot Jupiter orbiting extremely close to its star. Its atmosphere is intensely heated. But what makes worlds like this particularly valuable is that their atmospheres can be easier to study. When a planet crosses directly in front of its star, some starlight passes through the planet's atmosphere. The atmosphere changes the light. Tiny amounts. Almost unimaginably tiny. But modern telescopes can detect those changes. The star brightens and dims. The planet moves across the stellar disk. And hidden inside the changing light are clues. Water vapor, clouds, haze, other molecules. The atmosphere becomes a fingerprint. Imagine that. A planet hundreds of light years away, leaving a chemical signature in a beam of starlight. We cannot touch it. We cannot hear it. We cannot photograph its surface in detail. But we can read the light. The planet continues around its star. The observation ends. The star returns to its normal brightness. And somewhere on Earth, a computer begins turning those tiny changes into data. We drift away from WASP 79b. The planet becomes another point, and another strange world emerges. WASP 80b. This planet is a gas giant orbiting a relatively cool star. Its atmosphere has become interesting because its temperature falls between the extremely hot planets and the cooler gas giants. This gives scientists another opportunity to study how atmospheres behave across different temperatures. Temperature changes chemistry. Chemistry changes clouds. Clouds change how light interacts with the atmosphere. And all of these things influence what we see. Imagine floating above the planet. The atmosphere appears blue-green or hazy depending on the wavelengths of light we imagine reaching our eyes. Cloud layers drift slowly. The star appears smaller than our sun would from Earth. The planet turns. And somewhere far below, gases are moving under immense pressure. We remain high above the clouds. Nothing needs to happen quickly. A cloud forms. Another disappears. Heat moves. Molecules collide. The planet continues. And for a moment, the universe feels almost peaceful. Then we move on. A world called WASP 96b appears ahead. This planet became especially famous because observations of its atmosphere provided evidence of water vapor. But the planet itself is nothing like Earth. It is a hot gas giant. There is no reason to imagine blue oceans beneath those clouds. Instead, imagine a gigantic atmosphere filled with gases heated by a nearby star. As the planet crosses its star, starlight passes through the atmosphere. The atmosphere absorbs particular wavelengths. Scientists analyze those patterns, and water vapor reveals itself, not as rain, not as an ocean, but as molecules floating high above an alien world. This is one of the strangest things about water in the universe. Water does not have to mean an ocean. It can exist as vapor, as ice, as part of clouds, as molecules trapped within rocks, as high-pressure forms deep inside planets. Earth's water cycle is only one possible version. On another planet, water might never reach a surface. It might remain locked inside an atmosphere. It might exist beneath kilometers of ice, or it might be present only in tiny quantities. WASP 96b reminds us that discovering water is only the beginning. The question is not simply, is there water? The question is, where is the water, and under what conditions does it exist? We leave the planet behind, and another world appears. WASP 103b. This planet is particularly strange because it orbits so close to its star that the star's gravity can distort its shape. Instead of remaining a perfect sphere, the planet can become stretched. Imagine a giant gas world being gently pulled from both sides by gravity. Its shape becomes slightly elongated. The effect is subtle from far away. But on the scale of an entire planet, even a small distortion is extraordinary. Gravity is reshaping the world. The planet is not simply orbiting. It is being pulled. The star pulls one side more strongly than the other. The planet responds. Its atmosphere shifts. Its interior responds. Its shape changes. And yet the entire system remains stable enough to continue. We float beside it. The star fills part of our view. The planet appears slightly swollen. And the enormous gravitational relationship between star and planet becomes visible through geometry. Nothing is touching. The star and planet are separated by millions of kilometers. Yet gravity connects them. We drift away. and another planet waits. WASP 104b. This is a particularly dark-looking hot Jupiter. Its atmosphere absorbs a large portion of the light that reaches it. Imagine approaching a planet that barely reflects the light of its star. Against the darkness, it becomes difficult to distinguish. A nearly black world. The star shines nearby, yet the planet seems to swallow the light rather than reflect it. This is one of the strangest visual possibilities in planetary astronomy. A world can be enormous and still appear almost invisible. The universe contains planets that are bright because of reflective clouds. Others are dark because their atmospheres absorb incoming radiation. Some worlds may be almost black in visible light. Others might glow strongly in infrared. A planet's appearance depends on what kind of light we use to observe it. Human eyes see only a narrow portion of the electromagnetic spectrum. There is much more light around us that we cannot see. Infrared, ultraviolet, radio, X-rays, gamma rays. Different wavelengths reveal different aspects of a planet. A world that looks dark to our eyes might be shining brightly in infrared. A cloud in visible light might become obvious at another wavelength. So even the darkness can contain information. We pass the black planet. Its outline fades. The star disappears. And we continue through the galaxy. Ahead is another famous world. HD 209458b. This planet was one of the earliest hot Jupiters to be studied in extraordinary detail. It was also among the first exoplanets where atmospheric escape was observed. The planet's atmosphere extends outward. Stellar radiation pushes against it. Hydrogen and other particles can escape. The world is slowly interacting with the environment around its star. Imagine standing far away and watching the planet orbit. Every few days, it passes in front of its star. The star dims slightly, then brightens. The planet continues. Nothing dramatic happens from one orbit to the next, but the atmosphere is constantly responding to radiation. Over immense periods, the planet may lose material. This is how planetary evolution works. Not always through sudden events. Sometimes through countless tiny changes. One particle, then another, a billion particles, a trillion, a number too large to imagine. And time adds them together. The planet's story continues. We leave HD 209458b behind. Another star appears, and another strange planet comes into view. HD 17156b. This world follows an unusual, highly eccentric orbit. Instead of traveling around its star in a nearly circular path like Earth, its distance from the star changes dramatically. Imagine the planet moving outward into colder regions, then swinging inward toward its star. As it approaches, the radiation increases. The atmosphere heats. The planet accelerates. Then it moves away. The energy decreases. The atmosphere cools. The planet slows. And the cycle repeats. It is a planetary journey of extremes. Imagine the climate changing simply because the planet moves closer to and farther from its star. A year would not feel like one smooth season. Instead, there would be a dramatic transition. Far from the star, the planet becomes colder. Closer to the star, it becomes intensely heated. The entire planetary environment responds to orbital geometry. We watch the planet complete its journey. It swings outward. The star becomes smaller. The darkness grows colder. Then the planet begins falling inward again. The star grows brighter. The planet accelerates. And we leave before it reaches its closest point. Another world appears. HD 80606b. This planet has one of the most eccentric known planetary orbits. Its path takes it from a relatively distant region to an extremely close approach to its star. Imagine watching its sky during that journey. For most of the orbit, the star appears relatively small. Then, as the planet falls inward, the star grows rapidly brighter. The atmosphere receives an enormous increase in energy. Temperatures can change dramatically. The planet rushes around its star. Then it begins moving outward again. The heating event is intense. The atmosphere responds. Clouds can change. Winds can accelerate. And the planet carries the memory of that encounter as it returns to the colder part of its orbit. It is almost like a cosmic heartbeat. Cold, approach, heat, extreme brightness, then retreat, darkness, cold again, and again, and again. The orbit continues. We watch one cycle from a safe distance. Then we leave. Ahead is another strange planet, Corot 7b. This world was one of the early rocky exoplanets discovered close to its star. It is extremely hot. Its surface may contain molten rock. If it is tidally locked, one side could experience permanent stellar illumination while the opposite side remains dark. Imagine a planet where rock behaves almost like water. Lava could cover large portions of the day side. Minerals could vaporize into the atmosphere. The planet's surface could glow under the intense light of its star. And yet, on the night side, conditions could be dramatically colder. Material vaporized on the hot side might move toward cooler regions and condense. A strange mineral cycle could occur. Rock could evaporate. Mineral vapor could move, then solidify. A planet without oceans could still have a cycle. A planet without rain could still have precipitation. A planet without forests could still have weather. The word weather does not belong only to Earth. Weather is simply the movement and interaction of a planet's atmosphere and surface under energy. On Corot 7b, that weather could be made of rock. We move away. The glowing surface disappears, and the stars return. Now a much larger planet approaches. P2b. This world is massive and follows a somewhat eccentric orbit around its star. Its distance changes significantly. That means the amount of energy it receives changes too. The atmosphere can heat rapidly as the planet approaches the star. Then it cools as the planet moves away. The planet is another example of how orbit can shape climate. Two planets with identical atmospheres could experience completely different climates if their orbits were different. Distance matters. Orbital shape matters. Stellar brightness matters. Atmospheric composition matters. Clouds matter. Rotation matters. Magnetic fields may matter. And all these variables interact. A planet is a system. Not one number. Not one temperature. Not one color. It is a moving combination of physics. We continue. Another world appears. GJ 504b. Unlike the hot planets close to their stars, this is a giant planet far from its star. It is young. And because young planets can still retain heat from their formation, they can glow strongly in infrared wavelengths. Imagine a giant planet far from its star. The star is only a bright point in the sky. The planet itself is cold compared with the hot Jupiters we have visited, but it still emits its own faint thermal radiation. Its atmosphere may contain clouds. Its temperature is lower. Its environment is quieter. It is a reminder that planets do not need sunlight to produce heat. A young planet can carry leftover energy from its birth. The gravitational collapse that formed the planet generated enormous heat. That heat takes time to escape. For millions of years, sometimes longer, a young giant planet can remain warm. As the planet ages, it slowly cools. Its glow fades. Its atmosphere changes. Its internal energy decreases. So when we see a young planet glowing in infrared, we are seeing a piece of its childhood. A planet still warm from its formation. We drift away, and the young world becomes a tiny infrared point. The darkness surrounds us. Ahead is another planet, 51 Eridani b. This is another young giant planet, located relatively far from its star. Its atmosphere contains clues about its composition and formation. Young planets are particularly useful because they retain more of the heat generated during their birth. Their atmospheres can therefore be studied in ways that older, colder planets cannot. Imagine the planet glowing faintly against the darkness. Its star shines far away. The planet itself is barely visible in ordinary light. But in infrared, it stands out. A warm ember floating through the cold. We approach. The atmosphere appears deep and hazy. Clouds may drift high above the planet. The deeper layers remain hidden. The planet is enormous. Yet the star still dominates the system. Everything is held together by gravity. We leave it behind. Another faint glow appears. Beta Pictoris b. This young giant planet orbits a star surrounded by a disk of dust and debris. Imagine looking across the system. A bright young star. Around it, enormous amounts of material remain. Dust, rock, ice, fragments, perhaps the leftovers of planet formation. And moving through this environment is a young giant planet. It is still warm from its formation. Its atmosphere emits infrared radiation. Its orbit carries it through the developing planetary system. For a moment, imagine the system billions of years in the future. The dust may have cleared. The planet will have cooled. The system may look calmer. But right now, we are seeing a planetary system in a younger stage. A glimpse of what planetary systems may look like before they settle into maturity. Our own solar system was once like this. The young sun was surrounded by a disk of gas and dust. Planets were forming. Asteroids collided. Comets moved through the system. Earth itself was still becoming Earth. The calm solar system we know today is the result of billions of years of change. Beta Pictoris b gives us a glimpse into another chapter of that process. We drift onward. Another planet approaches, HR 8799b. This world is part of a remarkable planetary system containing several directly imaged giant planets. Imagine looking at the system from above. A bright star in the center. Several enormous planets orbiting at great distances. Unlike many exoplanets that are detected indirectly, some planets in this system can be directly separated from their star in images. That makes the system especially fascinating. We can imagine the planets as visible points around the star. Large worlds, young worlds, warm worlds, moving through a broad orbital system. It almost resembles a miniature version of a planetary family, but with giant planets occupying distant paths. One planet follows another. The star shines in the center. The system slowly rotates through the galaxy. We drift between the planets. For a moment, it feels as though we are inside a real planetary system. But the distances are enormous. Even within one planetary system, the worlds may be separated by hundreds of millions or billions of kilometers. Space remains mostly empty. The planets are islands, and the star is the distant center of their gravitational landscape. We continue. Another member of the same remarkable family appears. HR 8799c, a young giant planet. A world with an atmosphere that contains molecules such as carbon monoxide and water vapor. The planet is still warm from its formation. Its atmosphere is thick. Its gravity is powerful. And far above the clouds, the planet glows faintly in infrared. We watch it move. Slowly. Very slowly. At such great distances from its star, its orbital period is much longer than Earth's. A single orbit can take decades. Imagine watching the planet for your entire lifetime and seeing only a portion of its journey. Generations could pass while the planet completes one orbit. And yet, compared with the age of the universe, even that enormous period is brief. We leave HR 8799c. The star becomes smaller. The system disappears. And another unusual planet awaits. PDS 70b. This young giant planet is especially fascinating because it appears to be forming within a disk of material around its star. Imagine a planetary system still under construction. Dust surrounds the star. Gas moves through the disk. Gaps appear. And inside one of those gaps is a young planet. The planet is still gathering material. It is still growing. It is not a finished world. It is a planet in the process of becoming. This is perhaps one of the most extraordinary things we can witness. Instead of looking at an ancient planet, we are looking at a young planet during its formation. Gravity gathers dust and gas. Material falls inward. The planet becomes larger. Its atmosphere grows. Its orbit evolves. The surrounding disk changes. Eventually, the system may settle. But for now, everything is still moving. The star, the disk, the planet, the dust, the gas. The entire system is alive with motion. We drift quietly through the outer edge of the disk. The young planet glows faintly. Its star shines beyond. And for a moment, we are watching a world being born. We move onward. The darkness becomes deeper. And now we encounter another fascinating class of planet. A rogue planet. Unlike the worlds we have been visiting, a rogue planet does not necessarily orbit a star. It travels through interstellar space. Alone, dark, free from the warmth of a sun. Imagine approaching one. At first, there may be almost nothing to see. No bright star behind it. No reflected sunlight. Only a faint object moving through darkness. The planet may have been ejected from its original planetary system. Perhaps gravitational interactions with larger planets pushed it outward. Perhaps a passing star disturbed its orbit. Perhaps the planet formed independently from a collapsing cloud. There are different possibilities, but the result is the same. A world without a sun. A planet wandering through the galaxy. If it is a large gas giant, it could retain internal heat for a very long time. Its atmosphere could remain warm compared with the surrounding space. Its interior could continue generating heat. Far below the clouds, pressure would remain enormous. The planet would not necessarily be completely frozen. Instead, it could carry its own internal warmth through the darkness. Imagine floating above such a world. There is no sunrise, no sunset, no seasons caused by an orbit around a star. Only darkness. The stars would remain fixed in the distant sky as the planet traveled between them. Perhaps an aurora would occasionally illuminate the atmosphere. Perhaps clouds would move. Perhaps the planet would have moons. And those moons could provide a tiny local environment of their own. The rogue planet would continue moving. No destination, no central star, just gravity and momentum carrying it through the galaxy. We leave the lonely world behind, and for a moment, the darkness seems even larger, because now we understand something important. A planet does not necessarily need a star. Some worlds may exist in darkness. Some may have been born in darkness. Some may spend billions of years traveling through darkness. And perhaps there are enormous numbers of them. We continue. Another distant world appears. PSOJ 318.5-22. This object is particularly famous as a free-floating planetary mass object, a world without a normal host star. It is young. It still retains heat. And because there is no bright star overwhelming its light, astronomers can study its atmosphere in a different way. Imagine a young planet floating alone. Its atmosphere is warm. Clouds may form. Its internal heat radiates outward. There is no sunlight to illuminate its surface. Yet the planet still glows in infrared. It is almost like a cosmic ember, a world born without the usual spotlight of a star. We approach. The surrounding space is completely dark. No bright sun, no reflected light, only the planet's own faint warmth. Its atmosphere moves. Its clouds form. Its heat slowly escapes. And eventually, over immense stretches of time, the planet will cool. Its infrared glow will become weaker. Its atmosphere will change. The world will become colder. But it may continue wandering, a traveler without a destination. We drift away. The planet becomes smaller, and the darkness once again surrounds us. Yet this time, the darkness feels different, because we know there are worlds inside it. Invisible worlds, cold worlds, warm worlds, worlds without stars, worlds with 2 stars, worlds being torn apart, worlds still forming, worlds covered in clouds, worlds made strange by heat, and worlds that may be hiding oceans beneath kilometers of atmosphere. The universe is not empty. It is crowded with possibilities. We continue our journey. Ahead, another world appears. GJ 1214b returns to our thoughts as we pass another hazy, sub-Neptune-like planet. Its atmosphere remains difficult to interpret. Clouds and haze can hide deeper layers. Imagine the planet as a giant curtain. We can observe the outer surface of the curtain, but what lies behind it remains concealed. This is common in astronomy. Sometimes the obstacle is not distance. It is clouds. A planet can be relatively close and still hide its secrets behind a thick atmosphere. We look at the light. We examine spectra. We search for molecules. But if clouds block the signal, the deeper atmosphere becomes difficult to study. The planet remains mysterious. And perhaps that mystery is valuable. It reminds us that science does not always produce immediate answers. Sometimes the correct answer is simply, we do not know yet. There is something peaceful about that. The universe does not need to reveal everything at once. We can continue observing. We can build better telescopes. We can improve models. We can wait. And perhaps one day, the clouds will become transparent enough for us to understand what lies beneath. We drift away. Another world appears. GJ 1132b reminds us again of the strange relationship between rock and atmosphere. A rocky planet close to its star. A world under intense radiation. A place where the atmosphere may be continuously changing. Imagine a volcanic planet. Dark terrain. Hot regions. A thin atmosphere. Perhaps clouds of volcanic gases. The star shines above. The surface absorbs energy. The interior remains active. The planet is small, but its environment is extreme. And it shows us that rocky planets can have many different personalities. Earth is one. Venus is another. Mars is another. Mercury is another. And beyond the solar system are thousands more. Some may resemble Earth. Some may resemble Venus. Some may resemble nothing we have ever imagined. We move onward. The next planet appears. K2-141b returns to our path as another molten world. Its day side may contain oceans of magma. The surface glows beneath the star. Minerals can enter the atmosphere. Winds carry vapor across the planet. On the cooler side, material can condense. The cycle repeats. It is an entire weather system built from rock. Imagine looking at the horizon. Instead of an ocean stretching toward the distance, a glowing molten landscape extends beneath a dark atmosphere. Instead of rain falling from clouds, mineral particles may return to the surface. Instead of gentle winds, enormous atmospheric currents transport heat. It is a world where Earth-like words take on unfamiliar meanings. Ocean, rain, cloud, wind, night, day, all of them exist in some form. But none of them behave exactly as they do here. We leave the molten world. The glow fades, and the universe becomes quiet again. Another planet approaches. Kepler 10c. This world is particularly interesting because it is larger and more massive than Earth, while still being considered rocky or potentially rocky based on its density. It challenges simple categories. A planet can be larger than Earth without becoming a gas giant. It can contain substantial amounts of rock and possibly other materials. Its atmosphere could be thick. Its surface could be dramatically different from Earth's. The deeper we look at planets, the more we realize that categories are useful but imperfect. Rocky, gas giant, ice giant, super-Earth, mini-Neptune, hot Jupiter. These labels help us communicate, but nature does not have to respect the boundaries. There may be planets that sit between categories, worlds that are partly rocky and partly gaseous, worlds with enormous atmospheres over rocky interiors, worlds with deep oceans under thick envelopes, worlds that formed one way and later transformed into something completely different. Kepler 10c becomes another reminder that planetary diversity is enormous. We continue. A different star appears. Around it is Kepler 36b. This planet is famous because it orbits surprisingly close to another planet in the same system. Imagine standing on one of these worlds and looking into the sky. Another planet could appear enormous, much larger than our moon. Its surface might be visible as a disk. Clouds, continents, atmospheric patterns, perhaps even rings. The planets move around the same star in closely packed orbits. Their gravitational interactions can be significant, yet the system remains stable. Two worlds, very different sizes, very different environments, sharing the same star. Imagine watching the neighboring planet slowly move across the sky. It would become one of the most dramatic sights imaginable. A world that is not a moon, a true planet, another entire world hanging above you. The thought is almost dreamlike. And perhaps this is the perfect moment to let your imagination wander. Imagine lying somewhere on a quiet alien surface. The ground beneath you is warm. The atmosphere moves gently overhead. There are no cities, no roads, no artificial lights, only stars. And above the horizon, another planet hangs silently in the sky. You don't need to go anywhere. You simply watch. The planet moves. The stars remain. And time passes. We leave Kepler 36b behind. Another strange world emerges. Kepler 37b. This planet is very small, smaller than Earth. Its size makes it an important reminder that planets can be surprisingly tiny. For a long time, detecting such small worlds around distant stars was extremely difficult. The star is enormous compared with the planet. Imagine trying to detect a tiny grain of sand crossing in front of a giant spotlight from hundreds of light years away. That is essentially the challenge. Yet astronomers can detect these tiny worlds. A planet blocks a tiny fraction of starlight. The brightness changes. The pattern repeats. And suddenly, a planet exists in our catalog. Kepler 37b is small. It is close to its star. It is likely hot. But its discovery showed that small planets are not necessarily rare. They can be found. They can be measured. They can become part of our understanding of planetary systems. We drift past the tiny world. It almost disappears against the star. Then it crosses the star's light again. A tiny shadow, a tiny world, a huge discovery. We continue. And somewhere ahead is another planet waiting in the darkness. The universe is still unfolding around us. The stars continue shining. The planets continue orbiting, and our journey through these strange worlds is not yet finished. There are still more distant skies to cross, more impossible temperatures, more strange atmospheres, more wandering planets, more worlds with unfamiliar oceans, more planets whose surfaces may glow, more planets whose clouds hide entire environments beneath them. And as we drift deeper into the night, the next strange world slowly begins to appear. The tiny world disappears behind us. Its star becomes a distant point, and once again, the darkness stretches in every direction. There is something strangely peaceful about traveling through space this way. No engines roaring, no traffic, no sound at all. Only the quiet movement of worlds around distant stars. And ahead, another planet slowly appears. This one is Kepler 452b. It became famous because its star is similar to the Sun, and because the planet travels through a region where temperatures could potentially allow liquid water under the right atmospheric conditions. From far away, the planet would look like a faint sphere, but its real story is hidden. We do not know whether it has oceans. We do not know whether it has continents. We do not know whether its atmosphere is thin or thick. The planet is larger than Earth, and that difference alone could change everything. Its gravity could be stronger. Its atmosphere could be deeper. Its geological activity could follow a different path. And its star is older than our Sun. That means the planet has existed in a different stage of stellar history. Imagine standing beneath its sky. The sunlight would come from a star that looks familiar in some ways. Yet the world beneath your feet could be completely unfamiliar. Perhaps clouds move slowly across enormous oceans. Perhaps mountains rise above broad plains. Perhaps the planet is covered in ice. Perhaps it is dry and barren. From here, we simply cannot know. And sometimes the most fascinating planets are the ones that leave the greatest space for imagination. We continue onward. Another world appears. Kepler 438b. This planet is relatively close in size to Earth and orbits within the habitable zone of its red dwarf star. But red dwarf stars can behave very differently from the Sun. They can produce powerful stellar activity. Flares can erupt. Radiation can increase dramatically. A planet orbiting close to such a star may experience a very different space environment from Earth. Imagine the sky suddenly brightening as the star releases a powerful flare. The planet's atmosphere receives a burst of energy. Auroras may intensify. Upper atmospheric gases respond. Particles race through space. Then the star settles again. The planet continues. Quietly, patiently, the flare becomes a memory. But repeated stellar activity over billions of years can reshape a planet's atmosphere. A world can slowly lose gases. Its chemistry can change. Its surface conditions can evolve. The star is not simply a source of light. It is an active participant in the planet's history. We drift away from Kepler 438b. Its red star fades, and another planet approaches. Kepler 442b. This world is another super-Earth-sized planet orbiting within the habitable zone of a red dwarf. It receives a different amount of energy than Earth does. Its atmosphere, if substantial, could transform that energy into a climate very different from anything we know. Imagine clouds gathering over an alien ocean. The clouds are illuminated by a reddish star. The sunlight is softer. The colors of the landscape would be different. A familiar sunset might not exist. Instead, the star could slowly sink toward the horizon, bathing the clouds in unusual shades. The planet turns. The atmosphere circulates. And perhaps somewhere on the dark side, enormous auroras appear. We cannot know, but the possibility is enough to make the world strange. A planet does not have to be covered in lava or racing around its star to be mysterious. Sometimes the mystery is simply whether another world could have an environment that feels almost familiar. Almost, but never quite the same. We move onward. Another planet appears in the darkness. Kepler 62e. This world belongs to a planetary system with several known planets. The star is smaller and cooler than the Sun. The planet's orbit places it in a region where water might potentially remain liquid under suitable atmospheric conditions. Imagine looking toward the horizon. The star would appear smaller. The sky might have a different color. The atmosphere could be thicker. Perhaps oceans cover much of the surface. Perhaps clouds dominate the entire planet. A world like this reminds us how little information a distant point of light contains. From Earth, the planet might be nothing more than a tiny change in brightness. Yet behind that change could be an entire planet. A world thousands of times larger than the cities we build. A world with an atmosphere extending for hundreds of kilometers. A world with an interior reaching thousands of kilometers deep. All of that hidden inside a tiny signal. We leave it behind, and the darkness opens again. Ahead is another fascinating planet. Kepler 20. This small rocky planet orbits very close to its star. Its surface is likely extremely hot. The planet's year is extraordinarily short. Imagine a calendar where an entire year passes in only a few Earth days. The planet races around its star. The star dominates the sky. The surface receives intense radiation. Any atmosphere would have to survive a harsh environment. And because the planet is small, its gravity may make retaining a thick atmosphere difficult. It could be a bare, rocky world. A planet stripped down to its surface. Imagine looking across a barren landscape. No oceans. No forests. No familiar clouds, just rock beneath an intense stellar sky. The surface slowly rotates. The star moves across the sky if the planet is not tidally locked. And far above, the universe continues unchanged. We move away. The tiny rocky world becomes invisible. Another planet approaches. Kepler 20f. This world is larger than Kepler 20e and follows another close orbit around the same star. Two planets, one system, two very different worlds. Kepler 20e is smaller and hotter. Kepler 20f is larger. Their formation histories may have been connected. They began from the same planetary disk, yet their final environments became different. This happens everywhere. A planetary system can begin with similar ingredients, but small differences in distance, mass, composition, and migration can lead to enormous differences. One planet keeps an atmosphere, another loses it. One becomes a gas giant, another remains rocky. One freezes, another melts. Planet formation is not simply construction, it is evolution. We drift between the two worlds. One fades behind, the other moves ahead, and their star remains at the center. We continue. Another unusual planet comes into view. Kepler 22b. This world is larger than Earth and orbits within the habitable zone of a sun-like star. Its nature remains uncertain. It could possess a thick atmosphere. It could be covered in an ocean. It could have a rocky interior beneath layers of gas. Perhaps it is somewhere between these possibilities. Imagine a planet almost entirely hidden beneath clouds. The atmosphere extends far above the surface. Below the clouds, perhaps a global ocean stretches around the world. No continents, no large islands, just water. A blue planet beneath a pale sky. But a global ocean can behave very differently from Earth's oceans. The pressure would increase with depth. Temperature would change. Chemistry would become unfamiliar. At enormous depths, water could behave differently from the water in our oceans. The planet's interior might influence the ocean from below. Heat could rise. Minerals could dissolve. Currents could circulate. The entire world could become one enormous planetary ocean. Or perhaps there is no ocean at all. That is the difficulty. Without direct observations, imagination can only offer possibilities. We leave Kepler 22b floating behind us, and the stars continue. Another world appears. Kepler 61b. This planet orbits a red dwarf star and lies within a region where conditions might allow moderate temperatures under certain atmospheric assumptions. Red dwarfs are fascinating because they are so common. Most stars in the Milky Way are smaller and cooler than our Sun. That means many potentially interesting planets may orbit stars very different from ours. Imagine the galaxy filled with small red suns. Around some of them are rocky worlds. Some frozen, some hot, some with atmospheres, some without, some possibly carrying oceans. The galaxy would look very different from the perspective of such a planet. The central star would be reddish. The light would have a different balance of wavelengths. And if the planet were tidally locked, one side might always face the star. The permanent day side would receive continuous light. The night side would remain dark. Between them, a twilight region might circle the planet. A permanent sunrise, a permanent sunset, a ring of transition around an entire world. We drift through that imagined twilight. The star remains low on the horizon. The surface beneath us gradually changes from light to darkness. And there is no morning or evening, only one continuous transition. We leave. Another world appears. TRAPPIST-1b. This planet is part of one of the most remarkable compact planetary systems discovered. Several Earth-sized worlds orbit a small red dwarf star. The planets are packed relatively close together compared with the planets of our solar system. TRAPPIST-1b is the innermost world. It receives intense radiation. Its surface conditions may be extremely harsh, but the entire system is fascinating because so many planets share the same star. Imagine standing on one planet and looking upward. Another planet could be visible, then another. The system would feel crowded compared with our solar system. The planets follow compact orbits. Their gravitational interactions can reveal information about their masses and compositions. Each world affects the others. A tiny gravitational tug, a small shift in orbital timing, a subtle variation. Scientists can measure these changes, and from them, they can estimate planetary masses. The planets communicate through gravity. We drift outward. TRAPPIST-1b becomes smaller. Then another planet appears. TRAPPIST-1c. This world lies farther from the star than its neighbor. Its environment may still be harsh, but the system gives us an opportunity to compare planets that formed in the same stellar neighborhood. Same star, similar age, similar birth environment, different worlds. One may retain more atmosphere, another may lose it. One may have a different surface composition, another may have a different internal structure. The planets become a natural laboratory. Imagine placing several worlds side by side. They all began in the same planetary system, yet each tells a different story. We move farther outward. TRAPPIST-1d appears. This planet is smaller. Its orbit is farther from the star. Its received energy is different. Perhaps it has an atmosphere. Perhaps it lost much of it. Perhaps its surface is covered in rock. Perhaps water once existed there. Again, uncertainty follows us. And that uncertainty is not a failure. It is simply the current boundary of knowledge. Astronomy often begins with a tiny signal. Then comes a question. Then another observation. Then a better instrument. Then another question. The process continues. A planet that is mysterious today may become much clearer tomorrow. We continue. TRAPPIST-1e appears. This world has received particular attention because its size and position make it one of the more intriguing planets in the system. It receives a level of stellar energy that may allow interesting climates if it possesses an atmosphere. Imagine the planet from above. Dark oceans perhaps, clouds perhaps, a reddish star hanging over the horizon, the atmosphere reflecting faint light. If the world is tidally locked, the same hemisphere may always face its star. But a thick enough atmosphere could transport heat from the bright side to the dark side. Winds would flow, heat would circulate, clouds would move. The planet could have a permanent climate pattern rather than the familiar cycle of day and night. A world where time is measured differently, not by sunrise, not by sunset, but by orbital movement and atmospheric circulation. We drift over the dark hemisphere. The star is hidden beyond the horizon. The sky is filled with stars. Then, far away, the atmosphere glows faintly, perhaps an aurora, perhaps reflected light, perhaps simply our imagination. We continue. TRAPPIST-1f. Farther from the star. Colder. Potentially more capable of retaining volatile materials. If it has a thick atmosphere, it could trap significant heat. Clouds could reflect some stellar radiation. The planet's surface might remain hidden. Perhaps ice, perhaps ocean, perhaps rock. The world could be a deep, cold place. And yet its atmosphere might make conditions surprisingly different from what its distance alone suggests. This is why planetary temperature cannot be determined from distance alone. Atmospheres matter. Earth would be much colder without its atmosphere. Venus is dramatically hotter because of its dense atmosphere. Mars is cold partly because its atmosphere is thin. 3 rocky planets. 3 very different climates. And around other stars, the possibilities multiply. We leave TRAPPIST-1f. Another planet appears. TRAPPIST-1g. This world is even farther from the star. Its orbit is longer. Its environment may be colder. But if it has a substantial atmosphere, heat could be redistributed. The planet might contain ice. Perhaps an ocean beneath the ice. Perhaps thick clouds. Perhaps enormous atmospheric circulation. Imagine standing on its surface. The star is small in the sky. The light is dimmer than sunlight on Earth. The surrounding landscape is frozen. But beneath your feet, heat from the planet's interior continues to move upward. A hidden ocean could exist below layers of ice. The planet would appear frozen from above while remaining active inside. This possibility exists in our own solar system. Some icy moons may contain subsurface oceans. So a frozen surface does not necessarily mean a dead world. Sometimes the most interesting environment is hidden beneath the ice. We move onward. TRAPPIST-1h appears at the outer edge of the compact planetary system. This world receives the least stellar energy of the known TRAPPIST-1 planets. Its surface could be extremely cold. Ice may dominate. The atmosphere could be thin, or perhaps the planet retains gases that help insulate it. Imagine a world where the star is little more than a bright red point. The night side is almost completely dark. The surface is frozen. The atmosphere is thin and quiet. And still, the planet moves. Still, the planet has an orbit. Still, its interior retains heat. Still, gravity holds it together. Even a frozen planet is not truly motionless. Its interior may slowly change. Its surface may crack. Ice may shift. Tiny geological processes may continue. The universe has many forms of activity. Some are explosive. Others are almost impossibly slow. We leave TRAPPIST-1h. The entire system becomes distant. 8 worlds around one small star. 8 different environments. 8 different stories. And we continue deeper into the darkness. Another strange planet approaches. 55 Cancri. This is a super-Earth orbiting extremely close to its star. It is hot enough that its surface may be dominated by molten rock. Imagine a planet where an ocean is not made of water, an ocean of lava, a glowing surface beneath a black sky. The star dominates the horizon. The planet races around it. Its year lasts only a fraction of an Earth week. The surface receives enormous amounts of energy. If an atmosphere exists, it may contain vaporized minerals. Rock becomes gas. Gas moves. Then it cools. Minerals condense. The planet may have a cycle unlike anything on Earth. A rocky atmosphere. A molten surface. Mineral clouds. Perhaps a permanent volcanic glow. We approach the day side. The surface is bright. Molten regions shimmer. The atmosphere above them moves. Then we cross toward the darker hemisphere. The glow fades. The surface cools. Material condenses. And the contrast between light and darkness becomes enormous. We leave 55 Cancri E behind. Another planet approaches. KLT 9b. This is one of the hottest known exoplanets. It is so intensely heated by its star that molecules in its atmosphere can be broken apart. Imagine entering an atmosphere where temperatures are high enough to destroy many familiar molecules. The planet is less like a world with ordinary weather and more like an enormous natural laboratory of extreme chemistry. The star shines fiercely. The planet absorbs tremendous energy. Atoms and molecules collide at enormous speeds. Some compounds cannot survive. On the day side, temperatures are extreme. The night side may be cooler, but still extraordinarily hot. The planet is tidally influenced by its star. Heat moves through the atmosphere. Winds race across the planet. The chemistry changes from one hemisphere to another. Imagine watching the horizon. The star would be enormous. The sky would be bright. The atmosphere would glow. And the planet would exist at the edge of what planetary chemistry can tolerate. We move away. The star becomes smaller. The heat fades behind us. And another world appears. KLT 11b. This planet is a low-density, inflated gas giant. Its atmosphere is extended. Its gravity is relatively weak for such a large world. That makes it easier for the atmosphere to reach high altitudes. Imagine floating above its clouds. Below us is a vast atmosphere. Above us is space. There is no solid ground, only deeper and deeper layers of gas. As we descend, the pressure increases. The atmosphere becomes denser. The planet's interior remains hidden. We rise again. The world looks almost transparent around the edges. A giant sphere of gas suspended in darkness. We drift away, and another planet appears. KLT 20b. This world orbits close to a hot, bright star. Its atmosphere is strongly heated by stellar radiation. The star's ultraviolet light can create complex atmospheric chemistry. High above the planet, atoms and molecules interact with the radiation. The upper atmosphere becomes an active region. The planet's day side receives constant energy. The night side remains different. Heat flows. Winds move. Clouds form. The atmosphere responds. A planet does not have to be alive to be active. Physics provides plenty of motion. We continue. Another planet approaches. WASP 121b. This world is an ultra-hot Jupiter with an atmosphere so heated that metals and other materials can exist in vapor form. Imagine clouds made from substances that would normally be solid on Earth. Iron, magnesium, other minerals. On an alien world, intense heat can transform familiar materials. Rock can vaporize. Metal can become gas. The atmosphere becomes a strange mixture of elements. And on the cooler side, some of those materials may condense again. Imagine an atmospheric current carrying vaporized iron from the day side toward the night side. As it cools, the iron could condense. Tiny particles form. They become clouds. Then winds carry them back. A planetary weather cycle built from metal. We drift through the atmosphere. The star glows behind us. The planet's clouds shimmer. The chemistry is completely alien, yet the rules are familiar. Heat, pressure, gravity, condensation, evaporation. The same physics. Different world. We leave. Another planet emerges. WASP 76b. This world has become famous for the possibility of iron condensation on its cooler hemisphere. Imagine a planet where iron is vaporized on the day side. The planet is so hot that iron can exist in gaseous form. Strong winds carry the vapor toward the night side. There, temperatures fall. The iron condenses, and something resembling metallic rain may occur. Not water, not snow, iron. The idea sounds like science fiction. Yet planetary atmospheres can become so extreme that familiar materials behave in extraordinary ways. Imagine standing beneath such a sky. You would not see ordinary clouds. You might see a shimmering atmospheric haze. The star would dominate one side. The opposite hemisphere would be dark. And somewhere beyond the horizon, iron could be condensing from the atmosphere. The planet continues its orbit. The process repeats. Every orbit, every year, for millions of years. We drift away, and the strange metallic world disappears. Another planet appears. WASP 17b. This is a huge, low-density gas giant with an atmosphere so extended that it can be surprisingly easy to study during transit. The planet is enormous, but its density is low. It is almost like an inflated cloud wrapped around a planetary core. Its atmosphere contains molecules that scientists can detect through starlight. Clouds may contain unusual particles, tiny grains, haze, complex chemistry. The atmosphere is not empty space. It is a dynamic environment. Gas rises, gas falls, winds circulate, radiation changes molecules. Clouds form and disappear. And beneath all of it, the planet's gravity keeps the world together. We float above the clouds. The planet fills our view. Its curve stretches beyond the horizon. The atmosphere becomes thinner above us. And then, gradually, the world ends in space. No wall, no boundary, only a fading concentration of particles. We move away. Another star waits, and another planet, WASP 18b, returns in our thoughts as we pass another world where the star's gravity and radiation dominate everything. These planets are reminders that there is no single definition of planetary normal. A world can be huge. A world can be tiny. A world can be dark. A world can be molten. A world can be frozen. A world can wander without a star. A world can orbit two stars. A world can be surrounded by rings. A world can have an atmosphere thousands of kilometers thick. And somewhere beyond all the planets we know, there may be worlds even stranger. We continue. Another world appears. Lava world LHS 3844b once again comes to mind as we cross through another system of small rocky planets. The day side glows. The night side remains cold. There is little atmosphere to carry heat. The planet becomes a natural experiment in temperature contrast. One hemisphere receives constant radiation. The other faces space. If we could move from one side to the other, the environment would change dramatically. The star would rise nowhere on the night side. The surface would remain in darkness. But on the horizon, the edge of the illuminated world might glow faintly. A permanent sunset. A permanent sunrise. A boundary between worlds. We drift along that boundary. The star remains just below the horizon. The surface beneath us is neither fully bright nor completely dark. It is a narrow region of transition, perhaps the most peaceful place on an otherwise extreme planet. We continue. Another planet appears, TOI 700d. This world is close to Earth in size and orbits within the habitable zone of its red dwarf star. The planet has attracted interest because it provides another opportunity to study potentially temperate rocky worlds around small stars. Imagine a quiet planet beneath a reddish sun. Perhaps the surface contains oceans. Perhaps clouds gather. Perhaps ice covers one hemisphere. Perhaps the planet is tidally locked. If so, the star would remain in one part of the sky. The climate could be organized around the permanent location of the star. The atmosphere might carry heat from the day side to the night side. Winds would move. Clouds would form. The planet could become a world of permanent atmospheric circulation. We do not know exactly what exists there, but the possibility is enough. A distant planet, a distant star, a set of physical conditions that may permit liquid water. And perhaps, somewhere beneath those clouds, chemistry is happening. We drift away. The planet becomes smaller, and another world appears. TOI 700e. This planet is another intriguing world in the same system. Its discovery shows how a single star can host multiple small planets. Again, the system becomes a miniature laboratory. Different orbits, different temperatures, different amounts of stellar energy, different planetary histories. The planets formed around the same star, but they do not necessarily share the same fate. One may be rocky and hot, another cooler, another perhaps more atmospheric. The universe creates families of worlds, and then gives each one a separate story. We continue. The star fades. The next world emerges. TOI 715b. This is a super-Earth-sized planet orbiting within the habitable zone of a red dwarf. It is another reminder that the galaxy contains many worlds and regions where temperatures could potentially allow liquid water. But temperature alone is never enough. The atmosphere decides what happens next. A thick atmosphere could trap heat. A thin atmosphere could allow the surface to freeze. Clouds could reflect radiation. Ocean currents could move energy. The planet's rotation could create atmospheric circulation. Magnetic fields could influence how the star interacts with the atmosphere. Every factor matters. We drift above the planet. The surface is hidden beneath clouds. We cannot tell whether there is an ocean. We cannot tell whether there are continents. The clouds remain, and perhaps the mystery is exactly what makes the planet beautiful. We move away. The planet becomes a tiny point. Another one waits. LP 791 to 18d. This rocky planet is especially interesting because gravitational interactions with another planet in its system may influence its orbit and potentially produce tidal heating. Imagine a planet being gently squeezed by gravity. Its orbit changes. Its interior responds. Rock moves. Heat builds. Volcanic activity may occur. The planet could be geologically active even without being extremely close to its star. This is an important idea. A planet can be heated from within by gravitational interactions. The same basic principle operates on moons in our solar system. Tidal forces can stretch and compress a world. That movement generates heat. So even a distant planet can potentially have a warm interior if its orbital relationship is complicated enough. Imagine standing on LP 791 to 18d. The surface might appear rocky. Volcanic regions could glow. The sky could be dark. And beneath your feet, the entire planet might be slowly flexing. Gravity pulling. Rock responding. Heat emerging. A hidden engine inside the world. We leave it behind. And the stars continue. Another planet appears. TOI 1452b. This world is a super-Earth orbiting within the habitable zone of a small star. One possibility discussed for such worlds is that they may contain substantial amounts of water. Imagine an ocean planet. No large continents. No familiar coastlines. Only water stretching from horizon to horizon. Clouds moving above. A small star shining overhead. The ocean could be deep. Very deep. At the bottom, pressure would become enormous. Water could behave differently. The ocean floor might be hidden beneath kilometers of high-pressure material. The planet could be more water than rock at the surface. From space, it would appear almost entirely blue. But beneath the blue would be an unfamiliar interior. A world where water dominates the landscape. A world where the horizon is always ocean. We drift over it. Cloud shadows move across the surface. Waves appear tiny from this height. The planet turns slowly. And for a moment, the alien world seems almost peaceful enough to sleep beside. We continue. Another planet emerges. K2-18b appears again in our journey as a reminder of the strange worlds between Earth and Neptune. A planet can be too large to resemble Earth, but too small to resemble Neptune exactly. These intermediate worlds may be among the most common planets in the galaxy. Their atmospheres could be thick. Their interiors could be rocky. Their oceans could be deep. Their chemistry could be unfamiliar. They occupy a planetary category that our solar system does not contain. And perhaps that is why they feel so strange. We grew up with 8 major planets. But the galaxy has shown us that 8 planets are hardly enough to describe planetary diversity. There are thousands of confirmed exoplanets. And each discovery adds another variation, another size, another orbit, another atmosphere, another climate, another possibility. We continue into the darkness. And ahead, another strange world is waiting. A planet with an unusual color. A planet that does not behave the way its size suggests. A planet whose atmosphere may be escaping. A planet whose surface may be molten. A planet whose sky could contain clouds of minerals. The stars remain silent. The universe remains enormous. And our journey through these strange worlds continues, slowly carrying us deeper into the night. The distant glow of TOI 1452b slowly disappears behind us. The imagined ocean world becomes nothing more than another faint point of light. And ahead, the darkness opens into another enormous region of space. There are stars everywhere now. Some bright, some faint, some so distant that their light is barely visible. And somewhere among them, another strange planet is waiting. We approach slowly. The next world is GJ486b, a rocky planet orbiting a small red dwarf star. It is close to its star, completing its orbit in only a few Earth days. From our distant viewpoint, it looks small and quiet, but its environment is anything but quiet. The planet receives strong stellar radiation. Its day side could be extremely hot. Its night side could be dramatically different. If the planet is tidally locked, the same hemisphere always faces its star. Imagine one side of the planet glowing beneath constant red sunlight. The other side remains in darkness. Between them, there may be a narrow region of transition. The star never rises or sets in the ordinary way. There is no morning, no evening, only permanent day on one side and permanent night on the other. And somewhere around the planet, the atmosphere, if one exists, could be moving constantly. Hot gases rise. Cooler gases descend. Winds transport energy. The planet becomes a giant atmospheric circulation system. We drift toward the darker hemisphere. The star slowly disappears below the horizon. The surface becomes black. Far away, the illuminated side remains glowing. The planet turns beneath us. Yet the boundary between day and night never moves across the surface. It remains fixed, a permanent line dividing light from darkness. We leave GJ 486b behind, and another planet appears, GJ 357d. This world is larger than Earth and orbits within a region where temperatures could potentially allow liquid water under certain atmospheric conditions. The star is a red dwarf, smaller than the Sun, cooler than the Sun, and much closer to the planet. Imagine standing beneath its sky. The star would not look exactly like our Sun. Its light would have a different color. The landscape, if there were one, would be illuminated by a softer, redder light. Perhaps clouds would stretch across a dark ocean. Perhaps glaciers would cover the continents. Perhaps the planet would have a thick atmosphere. Perhaps there would be no atmosphere at all. We do not know, and that uncertainty follows us through the universe. Sometimes astronomy gives us beautiful images. Sometimes it gives us numbers. Sometimes it gives us spectra. And sometimes it gives us only possibilities. But possibilities are enough to remind us how many worlds remain unexplored. We continue. Another world appears. GJ 1132b once again reminds us how different a rocky planet can become when it lives close to its star. Its surface may be extremely hot. Its atmosphere may be thin or changing. Its interior may remain active. Imagine a rocky landscape beneath an enormous red sun. The rocks are dark. Some regions may be volcanic. The air is thin. There are no oceans, no forests, no familiar clouds. And yet the planet has weather. Heat moves. Gases circulate. Minerals can enter the atmosphere. The surface interacts with radiation. A planet does not need Earth-like conditions to have a dynamic environment. We move away. Another world appears. LHS 475b. This planet is close to Earth size and orbits a small red dwarf. Its discovery is another reminder that Earth-sized worlds can exist around stars very different from our Sun. The planet's atmosphere remains an important question. Does it have one? If so, how thick? What is it made of? Could it contain clouds? Could stellar activity have stripped most of it away? Imagine the planet from above. A dark rocky sphere. A red star behind it. A thin atmospheric glow around the edge. The planet is small. The star is small. The system feels compact. Yet the questions surrounding it are enormous. A tiny atmosphere could contain clues about the planet's history. Perhaps the atmosphere is ancient. Perhaps it formed later. Perhaps it is being lost now. Perhaps volcanic activity continues replacing gases that escape. The planet becomes a natural laboratory for understanding how rocky worlds evolve. We drift away. The red star fades. Another world appears. Speculoos 3b. This planet is another Earth-sized world orbiting an extremely cool red dwarf. Its orbit is incredibly short because it travels very close to its star. 1 year on this planet lasts only a few Earth days. Imagine celebrating birthdays every few days. The calendar would become almost meaningless. The planet races around its star. The star remains enormous in its sky because of the planet's close distance. The day side receives intense radiation. The night side may be permanently dark, and the planet's atmosphere, if present, could be strongly affected by stellar activity. The star itself is tiny compared with the Sun, but from the planet's surface, it would dominate the sky. We float above the illuminated hemisphere. The surface is dark beneath reddish light. The star hangs overhead. It never moves far from its permanent position. Then we cross toward the night side. The star disappears. The sky fills with distant stars. The planet is divided again. Light, darkness, heat, cold, and between them, a boundary. We continue. Another planet appears. LP 791 to 18c. This world is larger than its neighboring rocky planet. Its gravitational influence may help shape the orbit of the smaller world. The planets move around the same star. Their paths interact. Their gravity changes one another's motion. This is one of the quietest forms of communication in the universe. No sound, no signal, no message, only gravity. A planet moves slightly differently because another planet is nearby. A tiny change in timing, a tiny shift in orbit, but those changes can reveal the existence of worlds that cannot be seen directly. Astronomers can sometimes discover an unseen planet simply because another planet is moving strangely. Imagine that. Finding a world by watching another world wobble. The invisible planet announces itself through gravity. We drift between the two. The larger planet moves slowly. The smaller one follows its orbit. The star remains at the center, and the entire system continues its silent gravitational dance. We move onward. Another strange world appears. HD 219134b. This is a rocky planet located relatively close to Earth by exoplanet standards. It orbits very close to its star. Its surface is likely extremely hot. Because the planet is relatively nearby, scientists can study it in considerable detail compared with many distant worlds. Imagine approaching a rocky planet whose star dominates the sky. The surface is dry. The atmosphere, if present, is thin. The landscape is dark and rugged. Perhaps huge lava plains cover portions of the dayside. Perhaps the planet has mountains. Perhaps ancient craters remain from the early history of the system. There is no reason to assume that every rocky planet looks like Earth. Some may resemble Mercury. Others may resemble Venus. Others may have no solar system equivalent. We drift above the surface. The horizon curves gently. The star shines, and the planet rotates. Slowly, quietly, we leave. Another world appears. HD 40307g. This planet has been discussed as a potentially temperate super-Earth around a nearby star, but its true nature remains uncertain. The term super-Earth describes size or mass. It does not mean Earth-like. A super-Earth could be a rocky desert, a water world, a thick atmosphere planet, an icy world, or something else entirely. The label tells us how large the planet is. It does not tell us how it feels to stand there. Imagine approaching HD 40307g. Clouds obscure the surface. We cannot see beneath them. Maybe an ocean is hidden below. Maybe mountains. Maybe ice. Maybe a dense atmosphere. The planet remains silent. We continue. Another world appears. GJ 9827d. This planet is particularly interesting because it is part of a multi-planet system containing several small worlds. It is larger than Earth. Its atmosphere may be thick. Scientists have investigated whether planets in this size range may have water-rich compositions. Imagine a planet where water exists in forms we would barely recognize. At the surface, perhaps a deep ocean. Below it, enormous pressure. Far beneath the ocean, high-pressure phases of ice. Water can behave strangely when squeezed. It does not simply remain ordinary liquid forever. Pressure can rearrange its molecules into different structures. So a water-rich planet may contain layers of material that would be called ice even when temperatures are far higher than Earth's freezing point. The word ice describes a structure, not always a temperature. That means another planet could contain enormous quantities of ice deep inside, while having a warm ocean at its surface. We drift downward through the imaginary atmosphere. Clouds above, ocean below, pressure increasing. The world becomes stranger with depth. Then we rise again. The planet's atmosphere stretches across the horizon. We leave. Another planet waits. 55 Cancri F. Unlike the intensely hot inner planet in the same system, this world orbits farther from its star. Its environment is much colder. The contrast between planets in one system can be extraordinary. One world can be a molten furnace. Another can be a cold giant. Both orbit the same star. They formed from the same disk of material. Yet distance changed everything. We drift through the system. The star remains in the center. The planets follow different paths. One close, one distant. Different worlds, different climates, different histories. This is why planetary systems should not be imagined as simple copies of ours. Every system can be its own architecture. We continue. Another world appears. 55 Cancri D. This giant planet travels much farther from its star. Its atmosphere is colder than those of hot Jupiter's. Clouds may form from substances that would never survive in the hottest planetary atmospheres. The planet rotates slowly in the darkness. Its star appears distant. And far below the clouds, enormous pressure compresses the gases. We float above the atmosphere. The planet appears blue or pale, depending on the composition of its clouds. A giant world, cold by planetary standards, yet still warm enough inside to emit some infrared radiation. Its interior retains energy. Its atmosphere moves. Its clouds drift. We leave. Another world emerges. 51 Pegasi B. This planet holds a special place in the history of exoplanet discovery. It was one of the first confirmed planets found around a sun-like star. Before discoveries like this, scientists had already suspected that other stars might have planets. But finding one around a star similar to the Sun changed everything. Suddenly, the possibility became reality. A planet around another ordinary star. A giant planet orbiting extremely close. A hot Jupiter. And from that discovery came thousands more. We approach 51 Pegasi B. The planet is hot. Its orbit is short. Its star is familiar in some ways. But the planet itself is nothing like Earth. It races around its star. The star dominates its sky. Its atmosphere is heated. And yet its importance is not simply its physical environment. It is part of the story of how we discovered that planets are everywhere. A single world helped open the door to an entire field of astronomy. We drift away. Another planet appears. Proxima Centauri b. This world orbits the closest known star to our solar system. The star is a small red dwarf. The planet's orbit is close. The star is active, and the planet may experience intense stellar radiation. Yet it lies in a region where liquid water could potentially exist under suitable conditions. Imagine looking across the surface. Our sun would not dominate the sky. Instead, a small red star would provide the light. Perhaps the landscape would be dark. Perhaps oceans would reflect the faint reddish illumination. Perhaps clouds would move over rocky continents. Perhaps the planet has no atmosphere at all. The closest known exoplanet is still incredibly far away. Even light takes years to travel between its system and ours. So when we look toward Proxima Centauri, we are looking into another planetary neighborhood that remains physically distant despite being our nearest stellar neighbor. We drift closer in our imaginary journey. The planet becomes larger. The star glows. And for a moment, the distance between worlds seems smaller. Then we remember, space is enormous. We leave Proxima Centauri b behind. Another star appears. Another planet. Barnard's star b. This world is thought to be a small planet orbiting one of the nearest stars to the Sun. Its environment is likely cold because of its distance from its faint star. Imagine a dim world beneath a weak red sun. The surface may be frozen. The atmosphere may be thin. The star would provide little warmth. The planet could be a cold, rocky world moving through a quiet system. But even here, the interior may contain heat. Radioactive elements decay. The planet slowly cools. Perhaps geological activity continues. Perhaps not. The surface may hold ancient scars from impacts. Every crater would be a memory, a record of collisions from the system's history. We drift above the frozen landscape. The star hangs low. The sky is black, and the planet moves silently through space. We continue. Another world appears. Ross 128b. This planet orbits a relatively quiet red dwarf compared with some other active stars. Its distance and stellar environment make it an interesting candidate for studying potentially temperate rocky planets. Imagine a small red star rising over an alien landscape. The light is gentle. The planet may have an atmosphere. Clouds could gather. Perhaps an ocean. Perhaps deserts. Perhaps ice. Again, we cannot know. But there is something calming about imagining a world where the star is small and red, the sky is dark, and the landscape is quiet. No cities, no roads, no noise, just a planet turning through space. We leave. Another world appears. Lytton B. This planet is another nearby candidate for a potentially temperate rocky world. It orbits a red dwarf. Its star is much smaller than the Sun. The planet may receive enough energy for interesting climates if it retains a suitable atmosphere. Imagine standing beneath a sky lit by a red sun. The colors of the landscape would be different. The clouds might appear darker. The shadows could have unfamiliar tones. The star would look small, but its light would still shape the entire world. The planet would still have weather. Still have seasons if its orbit and axial tilt permit them. Still experience geological processes. Still carry the long history of its formation. A planet around a red dwarf is not necessarily a strange planet. But when compared with Earth, almost everything about its environment could be unfamiliar. We drift away. The star fades, and another world emerges. Wolf 1061c. This planet orbits a small red dwarf and lies close to the region where temperatures could potentially be moderate. The system contains multiple planets. Again, several worlds around one star. Imagine them moving through space. One closer, one farther, one warmer, one colder. The star at the center. The planets following their own paths. The system is a miniature gravitational clock. Every orbit repeats. Every planet influences the others. And the star slowly changes over time. We watch from above. The planets move like tiny points. Then we move onward. Another planet appears. Wolf 1061d. This world lies farther from the star. Its environment may be colder. Perhaps ice dominates. Perhaps the atmosphere is thick enough to trap heat. Perhaps not. The planet remains uncertain. But uncertainty is part of the story. Every unknown world represents a future observation, a future telescope, a future scientist, a future discovery. The universe is full of unanswered questions. We continue. Another planet appears. Teagardens Star B. This world is another Earth-sized planet orbiting a small red dwarf. It is relatively close to its star. Its environment could be strongly influenced by stellar activity. The planet may be tidally locked. If so, one side would permanently face the star. Imagine a permanent afternoon on one hemisphere, a permanent midnight on the other, clouds moving between them, heat circulating. The atmosphere, if present, becomes the planet's great transporter. It carries energy away from the star-facing hemisphere. Without such circulation, the temperature difference could become extreme. But with a sufficiently thick atmosphere, the planet might distribute heat. The exact climate depends on details we cannot yet measure. We drift through the permanent twilight. The star remains low. The surface fades into darkness. And somewhere beyond the horizon, another half of the world sits beneath continuous starlight. We leave. The red dwarf becomes a tiny point. Another strange planet approaches. Teegarden's star C. This neighboring planet is farther from the star. Its climate could be colder. Perhaps it retains an atmosphere. Perhaps ice covers the surface. The two planets form an interesting pair. Same star, different distances, different conditions. The system demonstrates how quickly climate can change with orbital position. A small change in distance can move a planet from relatively temperate conditions to a frozen environment. But atmosphere can complicate that picture. A thick atmosphere can warm. A reflective atmosphere can cool. Clouds can do both. The climate of a planet is never determined by one factor. We continue. Another world appears. Gliese 667 cc. This planet orbits a red dwarf that itself belongs to a multiple star system. Imagine the sky. One red star dominates. But other suns remain nearby in the cosmic neighborhood. They may appear as bright stars in the sky. The planet is part of a larger gravitational family. Its star belongs to a system containing multiple stars. The planet orbits one. Other stars remain distant. From its surface, the night sky could look extraordinary. Multiple suns, different brightnesses, different positions. The galaxy would feel much more crowded. We drift above the atmosphere. The primary star is visible. The other stars shine farther away, and the planet continues its orbit. A world under more than one sun. We move onward. Another planet emerges. Kepler 47d. This world is another circumbinary planet. Two stars lie at the center. The planet circles both. The stars orbit each other. The planet follows a much larger path. Imagine the sky from the planet. Two suns could appear, sometimes close together, sometimes farther apart. Their combined brightness changes. Shadows may overlap. A sunset could involve two stars disappearing at different times. The orbital geometry would be beautiful and strange. The planet does not have a single central star. It has a binary heart. We drift around the system. The stars move. The planet follows. And everything remains connected by gravity. We continue. Another circumbinary planet appears. TOI 1338b. This world orbits two stars. The system gained attention because the planet was discovered using the transit method. One star can pass behind the other. The planet can cross in front of either star. The brightness patterns become complicated. Astronomers watch carefully. A tiny dip in light appears. Then another. Then another. The pattern reveals a planet moving through a two-star system. Imagine watching from the planet. Two suns rise. The sky changes. The stars orbit one another. The planet follows its own path. And somewhere far away, someone notices a tiny change in brightness and realizes that a planet exists. We drift away. The binary system fades, and the universe becomes dark once more. There are still many worlds ahead. Some will be enormous, some tiny, some burning, some frozen, some surrounded by strange clouds, some carrying oceans, some carrying only rock, some orbiting stars, some wandering without them. And with every new planet, the universe becomes a little less familiar. We continue into the darkness, and another strange world begins to appear ahead. The darkness ahead slowly begins to change. At first, there is only a faint point of light, then another, then several more. They seem to emerge from the blackness one after another, like distant lanterns scattered across an endless ocean. We move toward them. The stars grow brighter, and somewhere among them, another world is waiting. This time, the planet belongs to a system that seems almost ordinary from a distance. One star, several planets, a quiet region of the galaxy. But as we approach, the world begins to reveal its strange character. It is a planet known as K2-18b. At first glance, it seems promising. It is larger than Earth. It orbits within the temperate region of its star, and observations have shown that it possesses an atmosphere containing molecules of great interest to planetary scientists. But K2-18b is not simply a larger Earth. It belongs to a category of worlds that may have no true equivalent in our solar system. It could be a sub-Neptune, a planet between the size of Earth and Neptune. Its atmosphere may be thick. Its surface, if it has one in the familiar sense, could be hidden beneath enormous layers of gas and cloud. Perhaps beneath those clouds lies a deep global ocean. Perhaps the pressure becomes so intense with depth that water changes into exotic states. Perhaps the atmosphere is hundreds of times deeper than the atmosphere we know. We cannot simply look at K2-18b and imagine continents. There may be no continents. There may be no exposed rock. There may be no familiar coastline. Instead, there could be an entire world hidden beneath clouds. A planet whose true surface is invisible from space. We drift closer. The star is a cool red dwarf. It is much smaller and dimmer than our sun. Yet from the planet, it dominates the sky. The atmosphere glows faintly around the edge. Clouds move slowly, and beneath them, an enormous mystery remains. What is happening below? Perhaps an ocean stretches around the entire planet. Perhaps the ocean is thousands of kilometers deep. At some depth, pressure becomes extraordinary. Water begins behaving differently. The molecules become compressed. The structure changes. Ice can exist even at temperatures that would feel incredibly warm to us. The deeper we travel, the less familiar the planet becomes. Eventually, we turn upward again. The clouds remain above us. The ocean remains below. And we realize that this entire planet could be a world where water dominates everything. A world with no recognizable continents. No familiar mountains. No dry land. Just atmosphere, ocean, pressure, and a hidden interior. We leave K2-18b behind. Its faint red star shrinks into the distance. Another world appears. Kepler 22b. This planet is larger than Earth and orbits within the habitable zone of a sun-like star. The word habitable makes the planet sound almost familiar, but the reality may be completely different. Habitable does not mean inhabited. It does not mean Earth-like. It simply means that under certain atmospheric conditions, temperatures could potentially allow liquid water to exist. Kepler 22b may be a rocky world. It may be a water world. It may have a thick atmosphere. It may have enormous oceans. It may be something we have never encountered in our own planetary neighborhood. Imagine approaching through the clouds. Below us, an ocean stretches toward every horizon. No continents appear. No mountains rise above the waves. The entire planet is blue. But the blue may not be anything like Earth's blue. The atmosphere could scatter light differently. Clouds could be enormous. The ocean could be deeper. The pressure beneath it could become immense. Perhaps strange forms of ice separate the ocean from the rocky interior. Or perhaps the planet has a solid surface beneath a shallower sea. We cannot tell from this distance. And that uncertainty gives the planet its mystery. We continue. Another star appears, and around it moves a planet called TRAPPIST-1e. This world belongs to one of the most remarkable planetary systems known. Several Earth-sized planets orbit a tiny red dwarf. They are packed surprisingly close together. From the surface of one world, neighboring planets might appear enormous in the sky. Imagine looking upward. Instead of seeing only a distant moon, you might see another planet occupying a significant portion of the heavens. Its continents, clouds, and oceans, if they exist, would become visible as patterns across the disk. And somewhere beyond it, another planet would appear. The entire planetary system could feel like a chain of neighboring worlds. TRAPPIST 1e is particularly interesting because its orbit lies in a region where temperatures may permit liquid water under suitable atmospheric conditions. The planet may be rocky. It may possess an atmosphere. It may have clouds, perhaps an ocean, perhaps ice, perhaps a combination of all three. But its star is very different from ours. A small red dwarf, dim compared with the sun, yet close enough to dominate the planet's sky. The planet may also be tidally locked. One hemisphere always facing the star, the other always facing away. Imagine the permanent day side. The red star hangs motionless in the sky. It never crosses the heavens. It never rises. It never sets. It simply remains there. The opposite hemisphere sees darkness forever, and between them is a region of eternal twilight, a place where the star would sit permanently near the horizon. If the atmosphere is thick enough, winds could carry heat around the world. Clouds could form. Rain could fall. Ice could accumulate. The planet could have a climate unlike anything on Earth. We cross the twilight zone. The star remains on one side. The dark sky stretches endlessly behind us. And for a moment, the planet feels almost peaceful. No sunrise, no sunset, only a permanent transition between light and darkness. We leave TRAPPIST 1e behind. Another member of the same strange system appears. TRAPPIST 1f. This world is farther from its star. Its environment may be colder. If it possesses a substantial atmosphere, heat could be redistributed. If it does not, the surface could be frozen. Imagine a frozen landscape beneath a dim red star. The ground stretches into the distance. Ice covers enormous regions. Perhaps cracks run across the surface. Perhaps beneath the ice lies liquid water. The star is weak. The sky is dark. Yet the planet continues to rotate, or remains tidally locked. Deep beneath the frozen exterior, the interior continues to release heat. The planet is not necessarily dead. It may simply hide its activity beneath layers of ice. We move onward. TRAPPIST 1g appears. This world is larger than Earth and farther from the star. Its atmosphere could be substantial. Clouds may hide the surface. Perhaps a thick atmosphere traps enough heat to keep parts of the planet warmer than expected. Perhaps it remains frozen. Perhaps enormous oceans exist beneath an icy crust. Again, the possibilities multiply. The same star can host worlds with radically different conditions. One may be hot, another temperate, another frozen, another dominated by atmosphere, another dominated by rock. The planetary system becomes a natural experiment, a laboratory created by gravity. We move farther away. Another planet appears, TOI 700d, an Earth-sized world orbiting a small red dwarf. Its location makes it particularly interesting because it receives an amount of stellar energy that could allow moderate temperatures under certain atmospheric conditions. Imagine descending toward it. The atmosphere catches the light of the red star. Clouds move across the planet. The surface below is hidden. Perhaps there are oceans. Perhaps continents. Perhaps ice. The planet is quiet, but its star is active. Red dwarfs can produce powerful flares. Sudden bursts of radiation can sweep across nearby planets. A planet's atmosphere must endure this stellar weather. Over millions or billions of years, such radiation can change the chemistry of the atmosphere. It can strip gases away, or transform them. The atmosphere becomes a shield, a history book, a record of everything the planet has experienced. We drift along the edge of the atmosphere. The star flashes in the distance. Then the planet turns beneath us. We leave. Another world waits. TOI 700e. This smaller planet also orbits the same star. 2 planets. 1 star. Similar neighborhood. Different orbits. Different possibilities. The system demonstrates how planets can occupy overlapping regions of space while experiencing very different environments. Perhaps one is warmer. Perhaps the other is cooler. Perhaps their atmospheres create completely different climates. The planets may interact gravitationally. Their orbits may slowly change. Their histories may influence one another. We drift between them. The star remains behind. 2 worlds move silently through the darkness. And then we move on. Another strange planet appears. WASP 12b. This world is one of the most extreme hot Jupiters known. It orbits incredibly close to its star. The planet is so close that its atmosphere can be severely distorted by stellar gravity and heat. The world is not perfectly spherical. Its outer atmosphere can stretch outward. Material can escape. The planet is slowly losing itself. Imagine approaching the atmosphere. There are no comfortable clouds. No gentle blue sky. The temperatures are enormous. Molecules are broken apart. Atoms collide. The atmosphere expands outward. And the star's gravity reaches across the planet. The world begins to resemble a stretched sphere. A planet being pulled apart by the very star it orbits. Over immense periods of time, atmospheric material can escape into space. The planet becomes a victim of its own orbit. Too close, too hot, too much radiation. And yet it continues. Orbit after orbit. The star rises, or rather, remains dominant. The planet races around it. We watch from above. A world slowly being consumed. Then we leave. Another hot Jupiter appears. WASP 17b. This planet is enormous, but its density is remarkably low. It is one of those inflated worlds that seem almost impossible when compared with Earth. The planet is swollen by intense heating from its star. Its atmosphere extends far outward. If we could somehow descend through its clouds, we would not immediately encounter solid ground. We would fall through gas, cloud after cloud. The pressure would increase. The temperature would rise. The atmosphere would become denser. The planet would have no obvious boundary where sky ends and ground begins. It would be like descending into an endless atmosphere, a world made enormous by heat. We rise again. From above, the planet looks like a pale sphere surrounded by faint atmospheric haze. We move onward. Another planet appears. WASP 76b. Here, the weather becomes truly extraordinary. The planet is extremely hot. Its day side may be hot enough for certain metals to vaporize. As material moves toward the cooler night side, those metals can condense. Imagine clouds containing vaporized iron. Imagine winds carrying iron vapor from the day side to the night side. Then imagine that iron condensing into droplets, a form of metallic rain. The idea sounds impossible, but under extreme temperatures and pressures, chemistry follows rules that are very different from those familiar on Earth. The planet's atmosphere becomes a giant chemical circulation system. Iron rises, iron travels, iron condenses, and iron may fall. We cross from the day side toward the night side. The star becomes smaller. The atmosphere cools. Vapor begins to condense. The planet's weather changes as we move. There is no ocean beneath us, no forest, no familiar rain, only a hot atmosphere filled with chemistry. We leave WASP 76b behind. Another world emerges. WASP 121b. This planet is another ultra-hot Jupiter. Its atmosphere reaches extreme temperatures. Water molecules can be broken apart. Atoms may exist in forms unfamiliar to Earth. The planet is so close to its star that its atmosphere can expand outward. Some gases may escape into space. The upper atmosphere becomes enormous. We approach the planet's edge. The atmosphere glows faintly. Gas rises away from the planet. The star pulls on it. The world is slowly losing material. But the process happens over enormous periods. Millions of years. Perhaps billions. A planetary lifetime is long compared with a human lifetime. What looks motionless to us can actually be changing continuously. We leave. Another strange world appears. KLT 9b. This planet is among the hottest known exoplanets. Its dayside temperature can become so extreme that molecules struggle to remain intact. The atmosphere is closer to the conditions of a stellar environment than to anything found on Earth. Imagine approaching. The star fills the sky. The planet is glowing. The atmosphere is violently heated. Molecules are destroyed and reformed. The distinction between planetary atmosphere and stellar chemistry begins to blur. KLT 9b is a reminder that planets can exist under conditions approaching those of stars. It is still a planet, but its atmosphere behaves in ways that seem almost stellar. We drift away. The light fades. Another planet appears. Kepler 16b. This world orbits two stars. It is sometimes imagined as a real-life version of a planet with a double sunset. But the actual orbital dynamics are even more fascinating. The planet circles both stars. The two stars circle each other. The planet's path must remain stable despite the gravitational pull of both. From above, the system looks like a cosmic dance. Two stars moving around a shared center. A planet following a larger orbit. The stars rise and set in changing patterns. Sometimes both may be visible. Sometimes one may disappear before the other. The shadows could move in unusual ways. The seasons could be unlike those on Earth. The sky itself would be a constantly changing spectacle. And yet the system is governed by the same force that keeps the moon around Earth. Gravity. We leave Kepler 16b behind. Another circumbinary world appears. Kepler 34b. Here again, two stars occupy the center. The planet circles both. But this system is not simply a copy of Kepler 16. Its orbital arrangement is different. Its stars have different masses. Its planet follows a different path. Every planetary system is unique. Even two systems containing binary stars can produce very different environments. We drift farther away. The stars shrink. The planet disappears. And the darkness returns. Ahead, another world begins to emerge. It is smaller, rocky, close to its star, but its surface may be unlike anything we have imagined. This is Corot 7b, one of the early discovered rocky exoplanets. Its orbit is extremely close to its star. Its surface temperatures can become enormous. The dayside may be covered in molten rock. Imagine a landscape without oceans of water. Instead, rivers of lava, lava plains, volcanic mountains, a sky filled with vaporized minerals. The planet could have an atmosphere created partly by the evaporation of its own surface. Rock becomes gas. Gas rises. The atmosphere cools. Minerals condense. They return toward the surface. A rocky world experiencing something like a mineral weather cycle. We fly above the glowing landscape. The surface shines beneath the star. There are no green forests, no blue oceans, no snow, only rock, heat, and motion. We leave. Another strange planet appears. 55 Cancri. This world is extremely close to its star. It is larger than Earth, and it may have a surface covered in an ocean of molten material. Imagine an entire planet where solid ground is rare, where the surface glows, where temperatures are high enough to transform rocks. The star would appear enormous. The sky could glow. The surface could radiate heat upward. And if the planet is tidally locked, the day side and night side could have dramatically different environments. The permanent day side might be a glowing furnace. The night side could be cooler. Between them, material could circulate. Perhaps lava flows. Perhaps clouds of vaporized rock. The planet would be less like Earth and more like a cosmic furnace. Yet it is only one planet among billions that may exist in the galaxy. We move onward. Another world waits. LHS 3844b. This rocky planet orbits extremely close to its star. It is probably one of those worlds where the surface has little or no substantial atmosphere. Without a thick atmosphere to move heat around, the day side and night side can become dramatically different. The star-facing hemisphere is scorched. The opposite hemisphere is dark. There is almost no atmospheric bridge connecting them. Imagine standing on the night side. The star is hidden. The surface is cold. Above you, the sky is black. Then imagine traveling toward the day side. The darkness gradually disappears. A faint red glow appears. The horizon brightens. Then the star emerges. The temperature rises. The landscape becomes illuminated. And the difference between the two hemispheres becomes almost impossible to imagine. One planet, two extremes. A permanent contrast between fire and darkness. We leave. Another planet appears. GJ 367b. This is a small rocky world orbiting very close to its star. Its density suggests that it may contain a large iron-rich interior. Imagine a planet with a proportionally enormous metallic core. The rocky outer layers may be relatively thin. Deep beneath the surface, iron dominates. The planet is small, but dense, compact, heavy for its size. It is almost like a planetary remnant. Perhaps much of its outer material was lost during its history. Perhaps violent impacts stripped away layers. Perhaps its formation was simply unusual. Whatever its origin, the planet reminds us that two rocky worlds of similar size do not necessarily have similar interiors. One could be rich in silicate rock. Another could be dominated by metal. The surface tells only part of the story. We continue. Another world appears. K2-141b. This planet is so hot that its atmosphere may contain vaporized rock. The day side can become hot enough for silicate minerals to evaporate. Imagine a planetary atmosphere made partly from the surface itself. Rocks heat up. They vaporize. The gas rises. Winds transport it. On the cooler night side, the vapor condenses. Perhaps mineral rain falls. Then the material may return toward the day side. A cycle of rock evaporation and condensation. A world where the weather is made from stone. We drift through its atmosphere. Below us, the surface glows. Above us, vaporized minerals move through the sky. The planet turns. The star remains fixed over the day side. And somewhere on the night side, clouds of minerals may be forming. We leave this furnace behind. Another planet waits. WASP 103b. This world is a hot gas giant orbiting incredibly close to its star. Its shape may be distorted by tidal forces. Instead of being perfectly round, the planet can become stretched. The star pulls on one side. The planet's own gravity pulls inward. The result is a world that is slightly deformed. A reminder that planets are not always perfect spheres. Gravity can reshape them. Heat can inflate them. Rotation can flatten them. Tides can stretch them. The universe is constantly sculpting worlds. We move farther away. Another planet appears. PAT P7b. This hot Jupiter has an atmosphere where winds may travel at tremendous speeds. The planet is tidally locked. Its day side faces the star. Its night side faces away. Clouds can move between the hemispheres. Heat flows. The atmosphere shifts. And the planet's brightness changes as different parts rotate into view. From far away, astronomers can sometimes detect these subtle changes. A planet too distant to photograph directly can still reveal its weather through changes in starlight. We watch the world turn. A brighter hemisphere faces us, then a darker one. The light changes slightly, a tiny rhythm from an enormous distance. We continue. Another planet appears, HD 189733b. This famous hot Jupiter has a deep blue appearance when viewed in certain wavelengths. But its blue color is not a sign of calm oceans. The planet is extremely hot. Its atmosphere is filled with high-speed winds. Particles in the atmosphere scatter light. The world looks beautiful from afar. But beauty can be deceptive. A planet can appear blue without having a single drop of liquid water. Its sky can look peaceful while violent winds race through the atmosphere. We drift closer. The clouds move rapidly. The star illuminates the atmosphere. The planet glows. Then we move away again. The blue world becomes a distant point. And ahead, another planet is waiting. The darkness around it seems deeper than before. The stars are becoming more numerous. We are moving into a region of space where every direction contains another possibility. Another atmosphere, another climate, another planetary history. And somewhere ahead, another world is beginning to reveal itself. Its surface is hidden. Its star is faint. Its orbit is strange. And as we approach, we begin to realize that the next planet may be one of the most unusual worlds we have encountered so far. The journey continues. Quietly, slowly, through an endless universe filled with planets that no human has ever touched, and perhaps worlds that no human will ever see. The strange planet ahead slowly grows larger. Its atmosphere catches the light of its distant star. At first, the world looks almost ordinary. A pale sphere, a faint glow around its edge, clouds moving across the upper atmosphere. But as we drift closer, the details begin to emerge. This is not a world built for comfort. It is WASP 107b, a planet that seems almost too large for the amount of material it contains. Its atmosphere is enormously extended. Its density is remarkably low. The planet is inflated, almost as though its atmosphere has been stretched outward by the heat of its star. We approach the upper clouds. There is no solid ground beneath us, only layers of gas. The atmosphere becomes thicker as we descend. Pressure increases. Temperature changes. The familiar idea of altitude begins to disappear. On Earth, a few kilometers of atmosphere separate the surface from space. Here, the atmosphere can extend much farther. The boundary between planet and space becomes almost indistinct. And deep below those clouds, something even more unusual may be happening. The pressure and chemistry can create conditions where molecules behave differently from anything we experience naturally on Earth. The planet is not enormous because it contains an enormous amount of rock. It is enormous because its atmosphere is so expanded. A giant world with an unusually light interior. We rise again. From above, WASP 107b appears almost fragile. A pale sphere surrounded by a huge envelope of gas. It looks delicate, but its atmosphere is held together by gravity. We leave it behind. Another world appears. WASP 69b. This planet is also a gas giant orbiting close to its star. But it may be losing its atmosphere in a remarkable way. A stream of gas can escape from the planet and stretch behind it. Imagine the planet moving through space with a giant atmospheric tail. The tail can extend enormous distances. Hydrogen and helium escape from the upper atmosphere. Stellar radiation pushes the material outward. The planet continues its orbit. The tail follows behind. From far away, it could almost resemble a comet. But the source is not a small icy body. It is a giant planet, a world slowly shedding itself into space. We drift through the tail. The gas is extremely thin. There is no visible boundary, only a faint stream of material stretching away from the planet. Eventually, that atmosphere will disperse, but the planet remains, at least for now. We leave WASP 69b behind. Another planet approaches, HAT P32b. This is another inflated hot Jupiter. Its atmosphere extends far above the visible body. The planet receives enormous amounts of energy from its star. Heat expands the atmosphere. The planet becomes larger than it would otherwise be. We approach its upper atmosphere. The star shines intensely. The clouds below glow softly. There is no solid surface, only an enormous gaseous envelope. The deeper we descend, the stronger the pressure becomes. Eventually, the atmosphere would become so compressed that our familiar understanding of gas would begin to fail. The planet's interior is hidden beneath layers of increasing pressure. We rise again. The planet's edge appears almost soft. Not a sharp boundary, a gradual transition from atmosphere to space. We move away. Another star appears. Another world. This time, it is HAT P7b. Its orbit is extremely close to its star. Its day side is heated to extraordinary temperatures. But the planet's atmosphere does not remain still. Winds can carry heat around the world. Clouds can form on the cooler regions. The atmosphere becomes a giant conveyor belt. Energy enters on one side. It moves. It cools. It radiates away. The entire circulation continues. We approach the day side. The star fills much of the sky. The clouds glow. The temperature rises. Then we move toward the night side. The star disappears. The atmosphere becomes darker. Some molecules can condense. Clouds change. The chemistry shifts. The same planet has two very different faces. We continue onward. Another world emerges. WASP 19b. This planet is another hot Jupiter with a very short year. Its orbit is so close to its star that the entire planetary system seems compressed. The planet races around its star. A single orbit passes quickly. Imagine watching the star from the planet. The star dominates everything. There is no familiar rhythm of seasons. No long year. The planet's orbital cycle is measured in days. The atmosphere is heated continuously. The surface, if we could somehow reach it, would be unimaginably hot. Yet the planet remains in motion. Its orbit repeats. Its atmosphere circulates. Its clouds form and disappear. A whole world changing continuously while appearing almost motionless from a distance. We leave. Another strange planet approaches. WASP 43b. We have encountered its name before, but now we drift deeper into its atmospheric world. The planet is tidally locked. One hemisphere faces the star. The other faces away. The day side is a furnace. The night side is dark. Between them lies a moving atmosphere. Imagine standing near the boundary. The star would remain near the horizon. The surface would receive only angled light. The sky would glow red. Behind you, the darkness would stretch across half the world. Above, clouds could race through the atmosphere. The temperature would change gradually as you moved. Perhaps this twilight region could be one of the least extreme places on the planet. Not necessarily comfortable, but compared with the permanent furnace and permanent night, the transition could be remarkable. We cross the boundary. The star fades. The planet becomes darker. Then we turn back. The star reappears. A world divided by its own orbit. We leave. Another planet waits. WASP 127b. This world is a low-density gas giant with an atmosphere that extends far beyond the planet's visible surface. Its star heats it, its atmosphere expands, and winds may race around the planet. Imagine clouds moving at tremendous speeds. The planet may have atmospheric structures that stretch across enormous distances. A storm on this world could be larger than entire continents on Earth. But there would be no continents, no mountains, no oceans, only gas. We drift above the clouds. The atmosphere appears smooth from far away. But beneath that smooth appearance, winds are moving constantly. The planet is never still. We leave it behind. Another world appears. KLT 11b. This planet is another extremely low-density gas giant. It is so inflated that its atmosphere is unusually easy to study. Starlight passes through the outer layers. The atmosphere leaves chemical fingerprints. Scientists can examine those patterns to learn what gases surround the planet. Imagine the planet crossing its star. The star dims. Not by much, but enough. A tiny change in brightness. Inside that change is a hidden atmosphere. We watch from far away. The planet moves. The star dims, then brightens again. The planet has passed. A world revealed through a shadow. We continue. Another planet appears. WASP 17b once again comes to mind as we travel through this region of hot, inflated worlds. But now we move toward another planet whose atmosphere contains a different mystery. WASP 39b. Its atmosphere is rich in chemical clues. Water vapor, clouds, photochemistry. Starlight interacts with the upper atmosphere and changes molecules. The star is not merely heating the planet. It is chemically transforming it. High-energy radiation can break molecules apart. The fragments react again. New compounds form. The atmosphere becomes a vast chemical laboratory. We drift through the upper layers. The star shines through. Molecules absorb certain wavelengths. Other wavelengths continue outward. A distant observer could detect those missing colors. The atmosphere leaves its signature. The planet is telling us what it contains without ever speaking. We leave. Another world appears. HD 80606b. This planet has one of the most unusual orbits among known exoplanets. Its path around its star is highly elongated. Instead of following a nearly circular orbit like Earth, it travels along a stretched path. This means its distance from the star changes dramatically, and so does the amount of energy it receives. Imagine the planet moving slowly through the cold outer part of its orbit. The star appears distant. The planet is relatively cool. Then the planet begins falling inward. Gravity accelerates it. The star grows larger. Radiation intensifies. Temperature rises. The planet rushes toward its closest approach. The atmosphere experiences a sudden burst of heating. Storms may erupt. Winds accelerate. The planet's environment changes dramatically. Then it swings away. The star becomes smaller. The planet cools. The cycle begins again. A planetary year becomes a journey between extremes. Cold, heat, rapid transition, then cold again. We watch the planet complete its orbit. It resembles a traveler repeatedly approaching a furnace and then retreating into the darkness. We leave HD 80606b behind. Another planet appears. HD 17156b. This world also follows a highly eccentric orbit. Its distance from the star changes significantly. Again, the climate can change as the planet moves. The star is distant, then closer, then distant again. A planet's orbit can become one of the most important factors determining its environment. Earth's orbit is relatively gentle, but not every planet has such a stable path. Some worlds travel through dramatically changing conditions. We continue. Another planet appears. GJ 504b. This world is different. It is a directly imaged giant planet located far from its star. Instead of discovering it mainly through tiny changes in starlight, astronomers have been able to observe the planet's own faint light. The planet is young. It still retains heat from its formation. That internal heat makes it glow in infrared wavelengths. Imagine approaching through the darkness. The star is behind us. Ahead, a faint pinkish glow appears. The planet is not illuminated only by its star. It is glowing because it is still warm. A young planet cooling slowly through space. Its atmosphere remains hot. Clouds may exist. The planet radiates energy. Over time, it will cool. Its glow will fade. But for now, it carries the warmth of its birth. We drift beside it. The planet is enormous. The star appears distant. The space between them is vast. Unlike the tightly packed systems we have visited, this world lives far from its star. A lonely giant. We move onward. Another planet appears. Beta Pictoris b. This is another young giant planet that has been directly imaged. It orbits a young star surrounded by a disk of material. The system is still evolving. Dust, gas, planetesimals, planets, all moving through the same young environment. The planet itself is enormous. It is hot from the energy retained since formation. It glows in infrared. We approach. The planet's atmosphere is thick. Clouds move. The young star shines. Far around the system, debris forms a disk. This is a planetary system still carrying traces of its youth. We drift through the darkness. The planet remains visible. Then it fades. Another world emerges. HR 8799b. This planet is part of a remarkable system containing multiple directly imaged giant planets. Imagine looking into the system. Several enormous worlds orbit the same star. They are far apart compared with the planets in many compact systems. Each world follows its own path. The system becomes a miniature universe. A star, multiple giant planets, dust, debris, gravity, time. We drift outward. One planet passes in the distance. Another follows. The star remains central. The planets move slowly because their orbits are enormous. A single year on one of these worlds can last decades, perhaps centuries. Imagine a planet where seasons change incredibly slowly. A summer could last for years. A winter could stretch across decades. The sky would appear almost unchanged over a human lifetime. Yet the planet would still be moving, always moving. We leave the system behind. Another world appears. HR 8799c. A giant planet orbiting farther from its star. Its atmosphere is warm. Its clouds are made from chemicals that behave differently under its conditions. Methane may be present. Carbon monoxide may be present. Water vapor may exist. The atmosphere is a mixture shaped by temperature and pressure. We descend through the clouds. The light is faint. The star is distant. The planet's own heat becomes important. The world glows in infrared. A young giant still cooling. We rise. The planet becomes a small point. We move onward. HR 8799d appears. Another giant. Another orbit. Another atmosphere. The system begins to feel like a family of enormous worlds. Different temperatures. Different distances. Different atmospheric compositions, and yet all connected to the same star. The planets are not isolated. Their gravitational interactions help shape their orbits. Their shared history ties them together. We continue. Another world appears. HR 8799e. This planet is closer to the star than some of its siblings. It receives more energy. Its atmosphere is warmer. Clouds behave differently. The planet's orbit is shorter. The system becomes a demonstration of planetary diversity within a single family. 4 giant worlds. 1 star. Different environments. Different histories. Different orbital periods. And perhaps different interiors. We drift away. The star becomes distant. The 4 planets become tiny points. Then the system disappears. Ahead, another star begins to glow. And this time, the planet approaching us is not a giant. It is small, rocky, dense, and extremely unusual. Mercury has taught us that small rocky worlds can possess enormous metallic cores. But this planet may push that idea even further. It is GJ 367b, a tiny world packed with iron. Its size is not much larger than Earth's moon, yet its density is remarkably high. Imagine a world whose interior is dominated by metal, a planetary core exposed closer to the surface than we might expect. Perhaps its history involved enormous collisions. Perhaps its outer layers were stripped away. Perhaps it formed from unusual material. The planet races around its star. Its year is extremely short. The star fills the sky. The surface is intensely heated. We drift over the planet. The horizon curves sharply. The world is small, but its gravity is enough to hold on to its remaining material. The surface is barren, dark, ancient, and beneath it lies a dense metallic interior. We leave. The planet disappears into the red glow of its star, and the journey continues. Ahead lies another system. This one contains a planet whose existence reminds us of something extraordinary. Not every planet needs to be large to be important. Not every planet needs to resemble Earth. Sometimes a tiny world can reveal something enormous about how planetary systems form. We approach. The star grows brighter. The planet crosses in front of it. A tiny shadow appears, then disappears. And somewhere far away, an astronomer sees that shadow and realizes that another world has announced itself. Quietly, for only a few hours, but enough. Enough to prove that somewhere in the darkness, another planet is turning. And beyond it, there are still more. Far more. The journey is not ending. It is only becoming stranger. Because the farther we travel through the universe, the more obvious one truth becomes. Earth is not the template for every planet. Earth is one possibility. A beautiful possibility. A familiar possibility. But only one. The universe has created worlds of fire, worlds of ice, worlds of gas, worlds of metal, worlds with oceans deeper than imagination, worlds with atmospheres that escape into space, worlds that orbit 2 stars, worlds that wander without any star at all. And somewhere ahead, hidden in the darkness, another planet is waiting to show us something we have never seen before. We move toward it. Slowly, quietly, the stars surround us. The planet grows larger, and its atmosphere begins to glow. The next world is waiting. The tiny shadow disappears from the face of the distant star. For a moment, everything becomes still again. Then the planet continues along its orbit. We leave it behind. There are still more worlds ahead. 30 more worlds waiting in the darkness. And the first of them begins to emerge now. It is WASP 96b, a giant planet moving around a star far beyond our solar system. From a distance, it looks like a pale sphere surrounded by an enormous atmosphere. But this world is not simply a giant ball of gas. Its atmosphere contains water vapor, not oceans, not rivers. Water suspended high above the planet in the form of vapor. The distinction is important. A planet can contain water without having a blue surface. The temperature here is high enough that water exists in the atmosphere rather than as familiar liquid seas. We drift through the clouds. The star shines through the upper atmosphere. Light interacts with molecules. Some wavelengths disappear. Others continue onward. Those tiny changes in starlight allow astronomers to study the atmosphere of a planet that no spacecraft has ever visited. The world becomes a chemical fingerprint, a distant atmosphere revealed through light. We rise above the clouds. The planet becomes smaller. Its star becomes brighter, and we move toward another world. Hat P12b. This planet is another gas giant, but its atmosphere gives it a very different character. It is relatively cool compared with the hottest worlds we have visited. Clouds can become important. The atmosphere absorbs and scatters light. The planet's appearance changes depending on the wavelengths we observe. From one distance, it might appear pale. From another, its atmosphere reveals deeper colors and chemical signatures. We approach the upper atmosphere. The clouds stretch across the entire planet. There is no continent beneath us, no ocean we could sail, only layers of gas becoming denser with depth. The deeper we go, the greater the pressure. The planet becomes an endless atmosphere. We rise again. The star remains distant. The planet continues its quiet orbit. We leave. Another world appears. Hat P23b. This planet races around its star in an extremely short orbit. Its proximity to the star makes it intensely hot. The day side receives enormous amounts of radiation. The atmosphere expands. Winds move heat. The planet becomes a furnace traveling through space. Imagine looking toward the star from its cloud tops. The star would dominate the sky. Its light would flood the atmosphere. The planet's night side would be dramatically different. If the planet is tidally locked, one hemisphere would remain permanently illuminated. The opposite hemisphere would remain permanently dark. Between them, atmospheric winds would attempt to redistribute the heat. A perpetual planetary battle between light and darkness. We drift along the terminator. The star hangs low. The horizon glows. Behind us, darkness. Ahead, heat. The planet turns beneath us. But the boundary remains tied to the star. We continue. Another strange world approaches. WASP 33b. This planet orbits a very hot, rapidly rotating star. The star itself is unusual. It is hotter and more massive than our sun. Its radiation floods the planet. WASP 33b receives extraordinary amounts of energy. The atmosphere becomes intensely heated. Chemistry changes. Molecules can be broken apart. Clouds may form from materials that would be solid under Earth's conditions. We drift above the day side. The star appears enormous. The atmosphere glows faintly. Winds race across the planet. Far below, the surface remains hidden beneath layers of gas. This is not a world where water defines the climate. Radiation does. Heat does. Chemistry does. We leave the hot world behind. Another planet appears. WASP 50b. This gas giant circles its star extremely quickly. Its year lasts only a few days. Imagine a world where the seasons, if any exist, would be part of an incredibly rapid orbital cycle. The planet receives intense stellar radiation. Its atmosphere is heated. Clouds move around the globe. The star remains close. The planet is trapped in a short orbital dance. We watch it complete another revolution, then another. From our perspective, the planet seems to race around its star. But the planet itself would experience each orbit as normal. There is no sense of time passing faster. The laws of physics remain the same. Only the scale of the orbit is different. We leave. Another world appears. WASP 52b. This planet is a hot Jupiter with an atmosphere that may contain clouds and complex chemical compounds. Its atmosphere is not simply transparent gas. Particles can scatter light. Molecules can absorb radiation. The sky may be hazy. We approach. The planet glows softly. Clouds cover the world. There is no visible surface. The atmosphere stretches toward the horizon. We move through the upper layers. Below us, pressure increases. The gases become denser. Eventually, the distinction between atmosphere and interior becomes meaningless. We rise. The planet becomes a distant sphere. Another star waits ahead. Another planet emerges. WASP 80b. This world occupies an interesting middle ground between hot and warm giant planets. Its atmosphere has been studied for molecules such as water and methane. Methane is particularly fascinating because its abundance depends strongly on temperature and atmospheric chemistry. The planet's atmosphere becomes a giant chemical equation. Heat changes one molecule. Pressure changes another. Radiation breaks another apart. The gases react. Clouds form. The atmosphere evolves. We drift above it. The planet appears calm. But beneath the clouds, chemistry never stops. The atmosphere is constantly responding to the star. We leave. Another world appears. HAT P18b. This planet is a gas giant with a relatively low density. Its atmosphere is expanded. Its gravity is gentle compared with many other giant planets of similar size. The world seems almost inflated. We approach the upper clouds. The planet has no solid surface. Only gas. The atmosphere extends outward. Light from the star passes through the outer layers. The chemistry becomes visible through spectroscopy. A distant observer can learn about the planet without ever touching it. We drift away. Another planet approaches. WASP 110b. This world is another gas giant orbiting close to its star. Its atmosphere experiences intense heating. The planet's day side absorbs stellar energy. The night side radiates heat away. Atmospheric circulation connects the two. We imagine crossing from one hemisphere to the other. The star becomes brighter. The air becomes hotter. Then the light fades. The temperature changes. The atmosphere carries energy around the world. The planet becomes a giant heat engine. We leave it behind. Another world appears. TOI 1231b. This planet is larger than Earth and belongs to the intriguing class of sub-Neptune worlds. It orbits a relatively cool red dwarf. Its atmosphere may contain clouds. Water vapor may be present. The planet is not necessarily a solid rocky world with oceans. Instead, it may have a deep atmosphere surrounding a smaller interior. Imagine looking down from space. The entire surface is hidden beneath clouds. No coastline, no continent, no obvious mountain range. Just atmosphere. The deeper you travel, the more pressure increases. The planet becomes less familiar. We rise again. The star appears behind the clouds. Then the planet fades into the distance. Another world waits. TOI 270b. This planet is smaller than its neighboring sub-Neptune world and orbits closer to its star. Its position gives it a warmer environment. The system contains multiple planets. Each occupies a different orbital distance. The star sits at the center. The planets form a sequence. One world closer, another farther, another larger, another smaller. It is like watching a natural experiment unfold. A single planetary system showing how different worlds can emerge from the same original disk of gas and dust. We drift between the planets. Their paths never appear to touch, but gravity connects them. Each planet gently pulls on the others. Their movements contain traces of their neighbors. We leave the system. Another world appears. TOI 178b. This planet belongs to a remarkable system containing multiple planets with unusual orbital relationships. The planets are close together. Their orbital periods can form patterns. One planet circles its star. Another follows. Their timing becomes connected through gravity. These orbital resonances are among the most beautiful mathematical patterns in planetary science. The planets do not need to touch. They communicate through timing. One completes a certain number of orbits, while another completes a related number. A gravitational rhythm develops. We drift above the system. The planets move. Again and again, a silent celestial clock. We continue. Another planet appears. TOI 178c. This world is part of the same fascinating system. Its size and density differ from some of its neighbors. That is important. Planets formed in the same system do not necessarily have identical compositions. One can be dense. Another can be light. One can have a thick atmosphere. Another may have almost none. The planets are siblings, but they are not twins. We leave the system behind. Another world emerges. Kepler 20. This planet is close to Earth's size. It orbits very close to its star. Its environment is likely extremely hot. Imagine a rocky planet where the star occupies a huge portion of the sky. The surface could be scorched. The atmosphere, if present, would be thin or transformed by intense radiation. The planet races around its star. Its year is extraordinarily short. A world that completes its journey around its sun before Earth's seasons have barely begun. We drift above the surface. The planet glows. Then we leave. Another world appears. Kepler 20f. This planet is also close to Earth's size, but it occupies a different orbit. Its distance from the star changes the amount of energy it receives. Again, two planets in the same system can have dramatically different environments. The inner planet is hotter. The outer planet is cooler. The star remains the same. Only distance changes. But that single difference can transform an entire planet. We continue. Another strange world approaches. Kepler 62e. This planet is larger than Earth and orbits within the habitable zone of its star. The possibility of water makes it intriguing, but its actual surface remains unknown. Imagine a cloudy world. A thick atmosphere, a dark ocean, perhaps islands, perhaps no land at all. The star is smaller and cooler than our sun. The light would feel different. The sky could have unfamiliar colors. If clouds exist, they could completely reshape the climate. The planet might be warm, or cold, or covered in ocean, or something else entirely. We cannot know from distance alone, and so we leave it as a mystery. Another world appears. Kepler 62f. This planet lies farther from its star. It receives less energy. Without a substantial atmosphere, it could be frozen. With a thick atmosphere, greenhouse warming could keep the surface much warmer. This is one of the most important lessons of planetary science. The habitable zone is not a guarantee. A planet's atmosphere matters. Its clouds matter. Its composition matters. Its geology matters. Its history matters. Two planets at similar distances can have completely different climates. We drift above Kepler 62f. The surface disappears beneath clouds. The planet remains silent. We continue. Another world appears. Kepler 69c. This planet was once considered a possible Earth-like world, but further studies showed that it may be very different from Earth. Its size is larger. Its orbit is different. Its atmosphere is unknown. It may be a warm, rocky world. It may have a thick atmosphere. It may be a world where water is scarce. The lesson is important. A planet can look promising from a distance while remaining completely alien up close. We leave. Another world emerges. Kepler 452b. Often described as an Earth cousin because of its size and orbit around a sun-like star, this planet is nevertheless different from Earth. It is larger. Its mass may be greater. Its atmosphere is unknown. Its surface is unknown. And its star is older than our sun. Imagine standing there. The star overhead would look familiar, a yellow-white sun, but the planet itself could be nothing like Earth. Perhaps continents, perhaps oceans, perhaps clouds, perhaps deserts, perhaps a thick atmosphere, perhaps a frozen surface. The similarity ends with the clues we can measure. Everything else remains hidden. We move onward. Another planet appears. Kepler, 1649c. This world is close to Earth's size and receives an amount of energy from its star that makes it especially interesting. Its star is a red dwarf. The planet may be tidally locked. One hemisphere could face permanent daylight, the other permanent night. If an atmosphere exists, winds could transport heat. Perhaps the twilight region is comparatively mild. Imagine walking along the boundary. The red star hangs permanently on the horizon. The sky behind you is black. Ahead, the landscape is illuminated. There is no sunrise, no sunset, only a permanent line between day and night. We leave. Another world approaches. Kepler, 186f. This planet is roughly Earth-sized and orbits within the habitable zone of its star. Its star is smaller and cooler than the Sun. The planet receives redder light. The landscape, if it exists, would look different beneath that illumination. A forest would not necessarily look green in the same way. An ocean would reflect a different spectrum. The sky would scatter light differently. The planet would be Earth-sized, but its world would still be alien. We drift through the atmosphere. Clouds move. The star glows red. The planet turns. We continue. Another strange world emerges. Kepler, 438b. This planet is close to Earth's size and receives significant stellar energy, but its star is an active red dwarf. Powerful stellar flares may have affected the planet's atmosphere. Imagine sudden bursts of radiation sweeping across the sky. The star brightens. The upper atmosphere responds. Particles collide. Chemistry changes. The planet's atmosphere must endure. If a magnetic field protects the planet, it may help shield the surface. If the atmosphere is thick, it may absorb much of the radiation. But if the atmosphere is thin, the surface could be exposed. A planet's star can therefore shape its entire history. We leave. Another world appears. Kepler, 442b. This planet is larger than Earth and orbits within the habitable zone of its star. It receives less stellar energy than Earth. Its atmosphere could potentially make the difference between a frozen world and a temperate one. Imagine clouds drifting above a dark ocean. The star is slightly cooler than the Sun. The light is softer. The planet moves slowly around its star. If an atmosphere exists, winds carry energy. If water exists, it could freeze. If greenhouse gases are abundant, some regions might remain warm. The possibilities are enormous. We cannot see the surface, so we continue. Another planet waits. Kepler, 1652b. This world is another candidate for a potentially temperate environment around a red dwarf. Its star is smaller than the Sun. Its orbit is closer. The planet receives its energy from a very different source. Imagine a world where the year is short. The star remains red. The sky is darker. The planet may be tidally locked. Again, one side could experience perpetual day, the other perpetual night. The twilight region becomes a place of constant transition. We drift along it. The red star hangs low. Clouds move overhead. The surface disappears beneath us. Then we move away. Another world appears. Kepler, 1229b. This planet is larger than Earth and orbits within the habitable zone of a red dwarf. Its environment could be cold or moderate depending on its atmosphere. The star provides less visible light than the Sun. The planet may receive much of its energy in infrared wavelengths. Imagine standing beneath a sky where the dominant star looks reddish. The world would not necessarily be dark. It would simply be illuminated differently. The atmosphere would absorb different wavelengths. The clouds would behave differently. The planet's chemistry would respond to its star. We leave. Another world emerges. Kepler, 1647b. This planet is much larger, and it is especially unusual because it orbits two stars. A circumbinary giant. Two suns. One planet. The stars orbit each other while the planet circles both. Imagine watching the sky. One sun rises. Another follows. Sometimes they appear close together. Sometimes farther apart. Their brightness changes. Their shadows overlap. The planet's seasons can become complex, but the system remains stable. Gravity balances the entire arrangement. We drift above the planet. Two stars shine beneath us. The world follows its enormous orbit. We move onward. Another planet appears. Kepler, 453b. Another circumbinary world. Again, two stars occupy the center. The planet circles both. But this world is smaller than many of the giant circumbinary planets we have encountered. Its orbit takes it through a changing gravitational environment. The two stars move around each other. The planet follows its own path. From its surface, the sky would never look quite the same. The stars would constantly shift positions relative to one another. Two suns could rise. One could set. The other could remain. The night could begin with one star still visible. A truly unusual sky. We leave. Another world appears. Kepler, 47b. This planet is smaller than Earth. It is another circumbinary world. Two stars. One small planet. A compact planetary system. The planet travels around both stars while they orbit each other. Its discovery showed that even small planets can exist in these complex environments. The universe does not require simple architecture. It can build planets around binary stars. It can build multiple planets around binary stars. It can build systems that remain stable despite all this motion. We drift away. The stars become distant. And now the final strange world begins to appear. It is not the largest, not the hottest, not the darkest, not the most distant, but it represents one of the strangest possibilities of all. A planet without a permanent home. A world that may wander between stars. A rogue planet. We cannot see its star because there is none. The darkness around us is deeper than before. There is no bright sun dominating the sky. No warm daylight. No familiar sunrise. The planet drifts through interstellar space. Perhaps it was once part of a planetary system. Perhaps a gravitational encounter with a giant planet threw it outward. Perhaps a passing star disturbed its orbit. Whatever happened, the planet escaped. Now it travels alone. Its surface may be frozen. Its atmosphere may be thin. But deep below, the story may be different. The planet's interior still contains heat. Radioactive elements slowly decay. Energy moves outward. If the planet has enough insulating material, heat could remain trapped beneath the surface. Perhaps a layer of liquid water survives beneath the ice. A hidden ocean in a world with no sun. Imagine descending beneath the frozen crust. The surface is dark. The atmosphere is silent. There is no sunlight. But deeper down, pressure rises. Heat increases. Ice changes. And perhaps, beneath kilometers of frozen material, an ocean exists. A dark ocean. An ocean that has never seen sunlight. An ocean warmed by the planet itself. If chemistry and energy sources exist there, the environment could be unlike anything on the surface. We rise again. The frozen exterior returns. The stars remain scattered across the black sky. No sun rises. No morning arrives. The planet simply continues moving. Alone. Silent. But perhaps not completely dead. And as we slowly pull away from this wandering world, the entire journey begins to come together. We have crossed worlds of molten rock, worlds covered in clouds, worlds with enormous atmospheres, worlds with strange metals, worlds with deep oceans, worlds orbiting two stars, worlds orbiting red dwarfs, worlds so close to their stars that their atmospheres escape, worlds so cold that oceans may hide beneath ice, worlds that are dense with iron, worlds that are light and inflated, worlds that race around their stars in only a few days, and worlds that may wander through darkness without a star at all. 100 strange planets. 100 reminders that the universe does not build worlds according to a single design. Some are familiar enough to make us wonder whether Earth-like environments might exist elsewhere. Others are so extreme that they seem almost impossible. But all of them tell us something. A planet is not simply a rock moving around a star. It is a history, a chemical system, a gravitational story, a climate, an atmosphere, an interior, a record of collisions, heat, radiation, and time. Every world we have visited tonight has been shaped by these forces. And every world still hidden from our telescopes will be shaped by them too. The universe is still producing surprises. New planets are being discovered. New atmospheres are being measured. New systems are being mapped. And somewhere far beyond the planets we know, another strange world is moving through the darkness. Perhaps it has an ocean. Perhaps it has clouds made of minerals. Perhaps it is covered in ice. Perhaps it circles two stars. Perhaps it is completely alone. We do not know yet. And that may be the most beautiful part. There are still mysteries waiting. Still worlds waiting. Still distant stars carrying planets that have never been named. So as the imagined journey slowly comes to an end, we drift farther away from the final world. The planets become small. The stars become points. The galaxy stretches around us. And Earth, our familiar blue world, becomes only one tiny planet among an almost unimaginable number of others. One world, one atmosphere, one ocean, one home, and somewhere in the darkness beyond it, countless other worlds continue their silent journeys. Orbiting, turning, cooling, burning, freezing, evolving, waiting, and perhaps, someday, another telescope will look toward one of those distant stars. A tiny shadow will cross its surface. A faint chemical fingerprint will appear. A strange signal will emerge. And once again, humanity will realize that the universe has created something we never expected. Until then, the planets remain out there, silent beneath their stars, hidden beyond the darkness. And for now, we can simply drift among them, slowly, quietly, as the distant lights of 100 strange worlds fade into the endless night. The tiny shadow disappears from the face of the distant star. For a moment, everything becomes still again. Then the planet continues along its orbit. We leave it behind. There are still more worlds ahead. 30 more worlds waiting in the darkness. And the first of them begins to emerge now. It is WASP 96b, a giant planet moving around a star far beyond our solar system. From a distance, it looks like a pale sphere surrounded by an enormous atmosphere. But this world is not simply a giant ball of gas. Its atmosphere contains water vapor, not oceans, not rivers. Water suspended high above the planet in the form of vapor. The distinction is important. A planet can contain water without having a blue surface. The temperature here is high enough that water exists in the atmosphere rather than as familiar liquid seas. We drift through the clouds. The star shines through the upper atmosphere. Light interacts with molecules. Some wavelengths disappear. Others continue onward. Those tiny changes in starlight allow astronomers to study the atmosphere of a planet that no spacecraft has ever visited. The world becomes a chemical fingerprint, a distant atmosphere revealed through light. We rise above the clouds. The planet becomes smaller. Its star becomes brighter, and we move toward another world. Hat P12b. This planet is another gas giant, but its atmosphere gives it a very different character. It is relatively cool compared with the hottest worlds we have visited. Clouds can become important. The atmosphere absorbs and scatters light. The planet's appearance changes depending on the wavelengths we observe. From one distance, it might appear pale. From another, its atmosphere reveals deeper colors and chemical signatures. We approach the upper atmosphere. The clouds stretch across the entire planet. There is no continent beneath us, no ocean we could sail, only layers of gas becoming denser with depth. The deeper we go, the greater the pressure. The planet becomes an endless atmosphere. We rise again. The star remains distant. The planet continues its quiet orbit. We leave. Another world appears. Hat P23b. This planet races around its star in an extremely short orbit. Its proximity to the star makes it intensely hot. The day side receives enormous amounts of radiation. The atmosphere expands. Winds move heat. The planet becomes a furnace traveling through space. Imagine looking toward the star from its cloud tops. The star would dominate the sky. Its light would flood the atmosphere. The planet's night side would be dramatically different. If the planet is tidally locked, one hemisphere would remain permanently illuminated. The opposite hemisphere would remain permanently dark. Between them, atmospheric winds would attempt to redistribute the heat. A perpetual planetary battle between light and darkness. We drift along the terminator. The star hangs low. The horizon glows. Behind us, darkness. Ahead, heat. The planet turns beneath us. But the boundary remains tied to the star. We continue. Another strange world approaches. WASP 33b. This planet orbits a very hot, rapidly rotating star. The star itself is unusual. It is hotter and more massive than our sun. Its radiation floods the planet. WASP 33b receives extraordinary amounts of energy. The atmosphere becomes intensely heated. Chemistry changes. Molecules can be broken apart. Clouds may form from materials that would be solid under Earth's conditions. We drift above the day side. The star appears enormous. The atmosphere glows faintly. Winds race across the planet. Far below, the surface remains hidden beneath layers of gas. This is not a world where water defines the climate. Radiation does. Heat does. Chemistry does. We leave the hot world behind. Another planet appears. WASP 50b. This gas giant circles its star extremely quickly. Its year lasts only a few days. Imagine a world where the seasons, if any exist, would be part of an incredibly rapid orbital cycle. The planet receives intense stellar radiation. Its atmosphere is heated. Clouds move around the globe. The star remains close. The planet is trapped in a short orbital dance. We watch it complete another revolution, then another. From our perspective, the planet seems to race around its star. But the planet itself would experience each orbit as normal. There is no sense of time passing faster. The laws of physics remain the same. Only the scale of the orbit is different. We leave. Another world appears. WASP 52b. This planet is a hot Jupiter with an atmosphere that may contain clouds and complex chemical compounds. Its atmosphere is not simply transparent gas. Particles can scatter light. Molecules can absorb radiation. The sky may be hazy. We approach. The planet glows softly. Clouds cover the world. There is no visible surface. The atmosphere stretches toward the horizon. We move through the upper layers. Below us, pressure increases. The gases become denser. Eventually, the distinction between atmosphere and interior becomes meaningless. We rise. The planet becomes a distant sphere. Another star waits ahead. Another planet emerges. WASP 80b. This world occupies an interesting middle ground between hot and warm giant planets. Its atmosphere has been studied for molecules such as water and methane. Methane is particularly fascinating because its abundance depends strongly on temperature and atmospheric chemistry. The planet's atmosphere becomes a giant chemical equation. Heat changes one molecule. Pressure changes another. Radiation breaks another apart. The gases react. Clouds form. The atmosphere evolves. We drift above it. The planet appears calm. But beneath the clouds, chemistry never stops. The atmosphere is constantly responding to the star. We leave. Another world appears. HAT P18b. This planet is a gas giant with a relatively low density. Its atmosphere is expanded. Its gravity is gentle compared with many other giant planets of similar size. The world seems almost inflated. We approach the upper clouds. The planet has no solid surface, only gas. The atmosphere extends outward. Light from the star passes through the outer layers. The chemistry becomes visible through spectroscopy. A distant observer can learn about the planet without ever touching it. We drift away. Another planet approaches. WASP 110b. This world is another gas giant orbiting close to its star. Its atmosphere experiences intense heating. The planet's day side absorbs stellar energy. The night side radiates heat away. Atmospheric circulation connects the two. We imagine crossing from one hemisphere to the other. The star becomes brighter. The air becomes hotter. Then the light fades. The temperature changes. The atmosphere carries energy around the world. The planet becomes a giant heat engine. We leave it behind. Another world appears. TOI 1231b. This planet is larger than Earth and belongs to the intriguing class of sub-Neptune worlds. It orbits a relatively cool red dwarf. Its atmosphere may contain clouds. Water vapor may be present. The planet is not necessarily a solid rocky world with oceans. Instead, it may have a deep atmosphere surrounding a smaller interior. Imagine looking down from space. The entire surface is hidden beneath clouds. No coastline, no continent, no obvious mountain range, just atmosphere. The deeper you travel, the more pressure increases. The planet becomes less familiar. We rise again. The star appears behind the clouds. Then the planet fades into the distance. Another world waits. TOI 270b. This planet is smaller than its neighboring sub-Neptune world and orbits closer to its star. Its position gives it a warmer environment. The system contains multiple planets. Each occupies a different orbital distance. The star sits at the center. The planets form a sequence. One world closer, another farther, another larger, another smaller. It is like watching a natural experiment unfold. A single planetary system showing how different worlds can emerge from the same original disk of gas and dust. We drift between the planets. Their paths never appear to touch, but gravity connects them. Each planet gently pulls on the others. Their movements contain traces of their neighbors. We leave the system. Another world appears. TOI 178b. This planet belongs to a remarkable system containing multiple planets with unusual orbital relationships. The planets are close together. Their orbital periods can form patterns. One planet circles its star. Another follows. Their timing becomes connected through gravity. These orbital resonances are among the most beautiful mathematical patterns in planetary science. The planets do not need to touch. They communicate through timing. One completes a certain number of orbits, while another completes a related number. A gravitational rhythm develops. We drift above the system. The planets move. Again and again, a silent celestial clock. We continue. Another planet appears. TOI 178c. This world is part of the same fascinating system. Its size and density differ from some of its neighbors. That is important. Planets formed in the same system do not necessarily have identical compositions. One can be dense. Another can be light. One can have a thick atmosphere. Another may have almost none. The planets are siblings, but they are not twins. We leave the system behind. Another world emerges. Kepler 20. This planet is close to Earth's size. It orbits very close to its star. Its environment is likely extremely hot. Imagine a rocky planet where the star occupies a huge portion of the sky. The surface could be scorched. The atmosphere, if present, would be thin or transformed by intense radiation. The planet races around its star. Its year is extraordinarily short. A world that completes its journey around its sun before Earth's seasons have barely begun. We drift above the surface. The planet glows. Then we leave. Another world appears. Kepler 20f. This planet is also close to Earth's size, but it occupies a different orbit. Its distance from the star changes the amount of energy it receives. Again, two planets in the same system can have dramatically different environments. The inner planet is hotter. The outer planet is cooler. The star remains the same. Only distance changes. But that single difference can transform an entire planet. We continue. Another strange world approaches. Kepler 62e. This planet is larger than Earth and orbits within the habitable zone of its star. The possibility of water makes it intriguing, but its actual surface remains unknown. Imagine a cloudy world, a thick atmosphere, a dark ocean, perhaps islands, perhaps no land at all. The star is smaller and cooler than our sun. The light would feel different. The sky could have unfamiliar colors. If clouds exist, they could completely reshape the climate. The planet might be warm, or cold, or covered in ocean, or something else entirely. We cannot know from distance alone, and so we leave it as a mystery. Another world appears. Kepler 62f. This planet lies farther from its star. It receives less energy. Without a substantial atmosphere, it could be frozen. With a thick atmosphere, greenhouse warming could keep the surface much warmer. This is one of the most important lessons of planetary science. The habitable zone is not a guarantee. A planet's atmosphere matters. Its clouds matter. Its composition matters. Its geology matters. Its history matters. Two planets at similar distances can have completely different climates. We drift above Kepler 62f. The surface disappears beneath clouds. The planet remains silent. We continue. Another world appears. Kepler 69c. This planet was once considered a possible Earth-like world, but further studies showed that it may be very different from Earth. Its size is larger. Its orbit is different. Its atmosphere is unknown. It may be a warm, rocky world. It may have a thick atmosphere. It may be a world where water is scarce. The lesson is important. A planet can look promising from a distance while remaining completely alien up close. We leave. Another world emerges. Kepler 452b. Often described as an Earth cousin because of its size and orbit around a sun-like star, this planet is nevertheless different from Earth. It is larger. Its mass may be greater. Its atmosphere is unknown. Its surface is unknown, and its star is older than our sun. Imagine standing there. The star overhead would look familiar, a yellow-white sun, but the planet itself could be nothing like Earth. Perhaps continents, Perhaps oceans, perhaps clouds, perhaps deserts, perhaps a thick atmosphere, perhaps a frozen surface. The similarity ends with the clues we can measure. Everything else remains hidden. We move onward. Another planet appears. Kepler, 1649c. This world is close to Earth's size and receives an amount of energy from its star that makes it especially interesting. Its star is a red dwarf. The planet may be tidally locked. One hemisphere could face permanent daylight, the other permanent night. If an atmosphere exists, winds could transport heat. Perhaps the twilight region is comparatively mild. Imagine walking along the boundary. The red star hangs permanently on the horizon. The sky behind you is black. Ahead, the landscape is illuminated. There is no sunrise, no sunset, only a permanent line between day and night. We leave. Another world approaches. Kepler, 186f. This planet is roughly Earth-sized and orbits within the habitable zone of its star. Its star is smaller and cooler than the Sun. The planet receives redder light. The landscape, if it exists, would look different beneath that illumination. A forest would not necessarily look green in the same way. An ocean would reflect a different spectrum. The sky would scatter light differently. The planet would be Earth-sized, but its world would still be alien. We drift through the atmosphere. Clouds move. The star glows red. The planet turns. We continue. Another strange world emerges. Kepler, 438b. This planet is close to Earth's size and receives significant stellar energy, but its star is an active red dwarf. Powerful stellar flares may have affected the planet's atmosphere. Imagine sudden bursts of radiation sweeping across the sky. The star brightens. The upper atmosphere responds. Particles collide. Chemistry changes. The planet's atmosphere must endure. If a magnetic field protects the planet, it may help shield the surface. If the atmosphere is thick, it may absorb much of the radiation. But if the atmosphere is thin, the surface could be exposed. A planet's star can therefore shape its entire history. We leave. Another world appears. Kepler, 442b. This planet is larger than Earth and orbits within the habitable zone of its star. It receives less stellar energy than Earth. Its atmosphere could potentially make the difference between a frozen world and a temperate one. Imagine clouds drifting above a dark ocean. The star is slightly cooler than the Sun. The light is softer. The planet moves slowly around its star. If an atmosphere exists, winds carry energy. If water exists, it could freeze. If greenhouse gases are abundant, some regions might remain warm. The possibilities are enormous. We cannot see the surface, so we continue. Another planet waits. Kepler, 1652b. This world is another candidate for a potentially temperate environment around a red dwarf. Its star is smaller than the Sun. Its orbit is closer. The planet receives its energy from a very different source. Imagine a world where the year is short. The star remains red. The sky is darker. The planet may be tidally locked. Again, one side could experience perpetual day, the other perpetual night. The twilight region becomes a place of constant transition. We drift along it. The red star hangs low. Clouds move overhead. The surface disappears beneath us. Then we move away. Another world appears. Kepler, 1229b. This planet is larger than Earth and orbits within the habitable zone of a red dwarf. Its environment could be cold or moderate depending on its atmosphere. The star provides less visible light than the Sun. The planet may receive much of its energy in infrared wavelengths. Imagine standing beneath a sky where the dominant star looks reddish. The world would not necessarily be dark. It would simply be illuminated differently. The atmosphere would absorb different wavelengths. The clouds would behave differently. The planet's chemistry would respond to its star. We leave. Another world emerges. Kepler, 1647b. This planet is much larger, and it is especially unusual because it orbits two stars. A circumbinary giant. Two suns. One planet. The stars orbit each other while the planet circles both. Imagine watching the sky. One sun rises. Another follows. Sometimes they appear close together. Sometimes farther apart. Their brightness changes. Their shadows overlap. The planet's seasons can become complex, but the system remains stable. Gravity balances the entire arrangement. We drift above the planet. Two stars shine beneath us. The world follows its enormous orbit. We move onward. Another planet appears. Kepler, 453b. Another circumbinary world. Again, two stars occupy the center. The planet circles both. But this world is smaller than many of the giant circumbinary planets we have encountered. Its orbit takes it through a changing gravitational environment. The two stars move around each other. The planet follows its own path. From its surface, the sky would never look quite the same. The stars would constantly shift positions relative to one another. Two suns could rise. One could set. The other could remain. The night could begin with one star still visible. A truly unusual sky. We leave. Another world appears. Kepler, 47b. This planet is smaller than Earth. It is another circumbinary world. Two stars. One small planet. A compact planetary system. The planet travels around both stars while they orbit each other. Its discovery showed that even small planets can exist in these complex environments. The universe does not require simple architecture. It can build planets around binary stars. It can build multiple planets around binary stars. It can build systems that remain stable despite all this motion. We drift away. The stars become distant. And now the final strange world begins to appear. It is not the largest, not the hottest, not the darkest, not the most distant, but it represents one of the strangest possibilities of all. A planet without a permanent home, a world that may wander between stars, a rogue planet. We cannot see its star because there is none. The darkness around us is deeper than before. There is no bright sun dominating the sky, no warm daylight. No familiar sunrise. The planet drifts through interstellar space. Perhaps it was once part of a planetary system. Perhaps a gravitational encounter with a giant planet threw it outward. Perhaps a passing star disturbed its orbit. Whatever happened, the planet escaped. Now it travels alone. Its surface may be frozen. Its atmosphere may be thin. But deep below, the story may be different. The planet's interior still contains heat. Radioactive elements slowly decay. Energy moves outward. If the planet has enough insulating material, heat could remain trapped beneath the surface. Perhaps a layer of liquid water survives beneath the ice. A hidden ocean in a world with no sun. Imagine descending beneath the frozen crust. The surface is dark. The atmosphere is silent. There is no sunlight. But deeper down, pressure rises. Heat increases. Ice changes. And perhaps, beneath kilometers of frozen material, an ocean exists. A dark ocean. An ocean that has never seen sunlight. An ocean warmed by the planet itself. If chemistry and energy sources exist there, the environment could be unlike anything on the surface. We rise again. The frozen exterior returns. The stars remain scattered across the black sky. No sun rises. No morning arrives. The planet simply continues moving. Alone. Silent. But perhaps not completely dead. And as we slowly pull away from this wandering world, the entire journey begins to come together. We have crossed worlds of molten rock. worlds covered in clouds, worlds with enormous atmospheres, worlds with strange metals, worlds with deep oceans, worlds orbiting two stars, worlds orbiting red dwarfs, worlds so close to their stars that their atmospheres escape, worlds so cold that oceans may hide beneath ice, worlds that are dense with iron, worlds that are light and inflated, worlds that race around their stars in only a few days, and worlds that may wander through darkness without a star at all. 100 strange planets. 100 reminders that the universe does not build worlds according to a single design. Some are familiar enough to make us wonder whether Earth-like environments might exist elsewhere. Others are so extreme that they seem almost impossible. But all of them tell us something. A planet is not simply a rock moving around a star. It is a history, a chemical system, a gravitational story, a climate, an atmosphere, an interior, a record of collisions, heat, radiation, and time. Every world we have visited tonight has been shaped by these forces. And every world still hidden from our telescopes will be shaped by them too. The universe is still producing surprises. New planets are being discovered. New atmospheres are being measured. New systems are being mapped. And somewhere far beyond the planets we know, another strange world is moving through the darkness. Perhaps it has an ocean. Perhaps it has clouds made of minerals. Perhaps it is covered in ice. Perhaps it circles two stars. Perhaps it is completely alone. We do not know yet. And that may be the most beautiful part. There are still mysteries waiting. Still worlds waiting. Still distant stars carrying planets that have never been named. So as the imagined journey slowly comes to an end, we drift farther away from the final world. The planets become small. The stars become points. The galaxy stretches around us. And Earth, our familiar blue world, becomes only one tiny planet among an almost unimaginable number of others. One world, one atmosphere, one ocean, one home, and somewhere in the darkness beyond it, countless other worlds continue their silent journeys. Orbiting, turning, cooling, burning, freezing, evolving, waiting, and perhaps, someday, another telescope will look toward one of those distant stars. A tiny shadow will cross its surface. A faint chemical fingerprint will appear. A strange signal will emerge. And once again, humanity will realize that the universe has created something we never expected. Until then, the planets remain out there, silent beneath their stars, hidden beyond the darkness. And for now, we can simply drift among them, slowly, quietly, as the distant lights of 100 strange worlds fade into the endless night. And now, after traveling across so many distant worlds, we slowly begin to leave the planets behind. The stars remain, the darkness remains, but the journey begins to feel different. At the beginning, each world seemed isolated. A strange planet here, a distant star there, a small point of light surrounded by darkness. But after traveling across 100 different planetary possibilities, something becomes clear. These worlds are not isolated stories. They are pieces of a much larger story. The story of how nature builds planets. The story of how stars create environments. The story of how gravity shapes worlds. The story of how heat moves through atmospheres and interiors. The story of how time can transform an entire planet. And perhaps most importantly, the story of how little we still know. Because every planet we visited raised another question. A hot world made us wonder how atmospheres survive. A cold world made us wonder whether hidden oceans could exist beneath ice. A water-rich world made us wonder how deep an ocean can become before water stops behaving like ordinary water. A gas giant made us wonder what lies beneath thousands of kilometers of atmosphere. A rocky world made us wonder how many different types of surfaces can exist. And a world orbiting two stars reminded us that even the sky itself can be different. We slowly drift backward. The planets become smaller. The systems separate. The individual stars begin blending into the larger background. And now we can see something extraordinary. There are planets everywhere. Not literally around every star, but enough that the galaxy no longer feels like a collection of empty stars. It feels like a vast collection of planetary systems. Some simple, some crowded, some young, some ancient, some calm, some violent, some warm, some frozen, some filled with gas, some made mostly of rock, and some that seem to exist somewhere between categories. For thousands of years, humans looked at the stars and wondered whether they had planets. We had no way to know. The stars were distant points of light. Their planets were too small and too faint to see. But eventually, technology changed that. We learned how to detect the tiny gravitational influence of a planet on its star. We learned how to measure the slight dimming that happens when a planet crosses in front of its star. We learned how to study the light passing through an atmosphere. And suddenly, worlds that had been invisible became measurable. A planet did not need to be photographed directly to announce itself. It could reveal itself through motion, through timing, through gravity, through light, through a shadow. Imagine that for a moment. Some of the worlds we have visited are so far away that no spacecraft will reach them for an unimaginably long time. We may never stand on their surfaces. We may never collect their rocks. We may never hear the sound of their winds. We may never see their sunsets with human eyes. And yet we can know that they exist. We can estimate their size, their mass, their orbital period, their temperature, sometimes even their atmospheric chemistry, all from tiny changes in light. The universe leaves clues everywhere. We only need to learn how to read them. And perhaps that is why strange planets are so fascinating. They are distant mysteries that still allow us to ask questions. Take the worlds that orbit incredibly close to their stars. We encountered many of them. Their years can last only a few days. Some complete an orbit in less time than we would spend on an ordinary vacation. Imagine living on one. The star would dominate the sky. The planet would race around it. The atmosphere would absorb enormous amounts of energy. The surface could become molten. Rocks could evaporate. Minerals could become atmospheric gases. Clouds could contain substances that would be solid on Earth. Rain might not be water. It might be metal. It might be minerals. It might be something that sounds impossible until the temperature and pressure are understood. These planets teach us that weather does not have to mean rain and clouds in the earthly sense. Weather is simply the movement and transformation of matter through an atmosphere. On Earth, water makes weather familiar. On another world, rocks can become weather. Metals can become weather. Hydrocarbon compounds can become weather. The atmosphere becomes a laboratory. And then there are the worlds that are much colder. Worlds orbiting far from their stars. Worlds receiving little energy. Worlds where ice may cover enormous portions of the surface. But even these worlds can surprise us. Cold on the surface does not necessarily mean frozen everywhere. A planet can hide heat beneath its crust. A thick layer of ice can act like insulation. A rocky interior can release energy. Radioactive elements can slowly produce heat. Tidal forces can squeeze a planet's interior. And somewhere beneath a frozen exterior, liquid water may survive. We have seen hints of such environments within our own solar system. So when we imagine distant icy planets, it is not unreasonable to wonder whether some might contain hidden oceans. Perhaps enormous oceans. Oceans that have never seen sunlight. Oceans trapped beneath kilometers of ice. Oceans warmed from below. And that brings us to one of the most beautiful questions in planetary science. Could life exist somewhere we would never expect? We do not know. And tonight, we are not going to pretend that we do. A planet being in a habitable zone does not prove life exists. Water does not prove life exists. An atmosphere does not prove life exists. Organic molecules do not prove life exists. Even a potentially Earth-like world would still require careful investigation before we could make such a claim. But the possibility is enough to make these worlds important. Because for the first time in human history, we know that there are planets around other stars. We know that some are roughly Earth-sized. We know that some orbit at distances where temperatures could potentially permit liquid water. And we know that planetary systems are extraordinarily diverse. The search has only begun. Perhaps the next great discovery will not be another hot Jupiter. Perhaps it will be a small rocky planet with an atmosphere unlike anything we have measured before. Perhaps a telescope will detect a combination of gases that raises a fascinating question. Perhaps we will discover a world covered in clouds. Perhaps an ocean planet. Perhaps a planet with continents. Perhaps something completely unexpected. The history of astronomy suggests that the universe usually has something stranger waiting. We have already seen that. When the first hot Jupiters were discovered, they surprised scientists. Large planets orbiting incredibly close to their stars were not what many researchers expected. Then we found super-Earths, then sub-Neptunes, then compact planetary systems, then circumbinary planets, then planets with escaping atmospheres, then worlds with extremely unusual densities. Each discovery expanded the range of possibilities. And each time we thought we were beginning to understand the population of planets, another strange category appeared. Perhaps that pattern will continue. Maybe there are entire classes of worlds we have not discovered yet because our current instruments are not sensitive enough. There could be planets around faint stars, planets with unusual atmospheres, planets in distant parts of their systems, planets hidden by stellar activity, planets that do not transit from our viewpoint, planets whose existence can only be detected through gravity. The galaxy does not arrange its planets for our convenience. We see only the worlds whose signals happen to reach us in measurable ways. That means our current catalog is not a complete map. It is a collection of clues, a small window into an enormous population. We continue drifting through the darkness. The Milky Way stretches across the distance. Millions of stars appear, then millions more. And each one is another possibility. A star may have one planet, or several. Some may have dozens of bodies. Some may have planets orbiting extremely close. Some may have distant giants. Some may have worlds that migrated inward. Some systems may have experienced collisions. Some may have lost planets entirely. Some may have planets that were ejected into interstellar space. The architecture of a planetary system is the result of history. Gravity does not simply create a neat arrangement and leave it untouched. Planets pull on one another. Stars move. Asteroids collide. Comets migrate. Orbits change. Atmospheres escape. Volcanoes erupt. Ice melts. Water freezes. Radiation transforms molecules. Time reshapes everything. A planet that looks stable today may have looked completely different billions of years ago. Consider a young planet. Its surface may be molten. Its atmosphere may be thick with gases released from its interior. Asteroids and comets may still be striking the surface. The star may be more active. The planet may be changing rapidly. Then millions of years pass. The surface cools. A crust forms. An atmosphere evolves. Oceans may appear. Continents may develop. The planet becomes more stable. But even stability is temporary. Billions of years later, the star changes. Its brightness evolves. The planet's atmosphere responds. The climate changes. Perhaps the oceans disappear. Perhaps the atmosphere escapes. Perhaps the planet becomes frozen. A world is never just one thing. It is a sequence, a story written over billions of years. And that is true even for Earth. We sometimes imagine our planet as a permanent object, but Earth has changed dramatically. Its continents have moved. Its atmosphere has changed. Its oceans have changed. Its climate has changed. Its life has changed. The planet beneath us has never been completely still. So when we look at strange planets, we should remember that we are often seeing only one moment in a very long story. A hot planet today may once have been cooler. A planet with an atmosphere today may lose it in the future. A frozen planet could once have had oceans. A world that seems empty may once have experienced enormous geological activity. And a planet that appears quiet may still be changing deep beneath its surface. We drift farther. The individual planets become distant. Now the stars themselves begin to look like points. And perhaps this is a good time to think about scale. Earth is enormous to us. The oceans are enormous. The continents are enormous. The distance from one side of the planet to the other is difficult to imagine. But from space, Earth is a tiny sphere. The solar system is larger still. The distance between Earth and the Sun is already difficult to comprehend. Then come the outer planets. Then the Kuiper Belt. Then the vast distance to the nearest stars. Then the galaxy. And beyond the galaxy, countless other galaxies. The planets we have explored in imagination today are scattered across only a tiny part of this cosmic scale. Some are dozens of light years away, others hundreds, others farther still. Their light began traveling toward us long before it arrived. When we observe them, we are seeing the past. A distant planet may have changed since the light we receive left its system. The world we imagine tonight is therefore partly a memory, a snapshot carried across space. The universe itself becomes a time machine. Every distant star is an old message. Every distant planet is part of a story that has been traveling toward us. And when we look farther away, we look farther into the past. This means that somewhere out there, a planet may already have changed dramatically since the light we are currently receiving left its atmosphere. Perhaps its star has changed. Perhaps its atmosphere has escaped. Perhaps its surface has frozen. Perhaps a collision has transformed it. Perhaps nothing significant has happened. We simply do not know. And perhaps that uncertainty is comforting. Not everything needs an answer tonight. Some mysteries can remain mysteries. You can let them drift away, like the planets themselves. The hot worlds can drift away. The cold worlds can drift away. The gas giants can drift away. The water worlds can drift away. The strange red dwarf planets can drift away. The worlds around two stars can drift away. The lonely rogue planets can drift away. And the enormous distances between them can become quiet. The universe does not need to be understood all at once. It can simply be experienced. A star, a planet, a distant glow, another star, another world, another possibility, and another. We begin moving back toward our own planetary system. The distant stars remain behind us. The imaginary journey reverses. World after world becomes smaller. The enormous planetary systems disappear into the background. The galaxy becomes less overwhelming. And eventually, a familiar star begins to appear. Our sun. At first, it is only another star. But as we approach, it becomes brighter. The planets of our solar system begin to appear. First the inner regions, then the outer worlds. The familiar architecture returns. Mercury, Venus, Earth, Mars, the giant planets farther away, the smaller icy worlds beyond them. And somewhere among all of these familiar objects is the world we call home. Earth. From a distance, It looks simple. A small blue sphere. Clouds. Oceans. Continents. A thin atmosphere. But after everything we have seen, Earth may appear differently now. It is no longer simply the place we started. It is a planet. One planet among many. And yet it is extraordinary. Its atmosphere allows liquid water to remain stable across enormous regions. Its surface contains oceans and continents. Its temperature range supports complex chemistry. Its magnetic field helps shield the atmosphere from the solar wind. Its atmosphere protects the surface from much of the sun's harmful radiation. Its interior remains active. Its surface changes. And life has transformed the planet in ways we can see from space. After seeing worlds covered in clouds, we appreciate clear skies. After seeing lava planets, we appreciate cool ground. After seeing frozen worlds, we appreciate liquid water. After seeing worlds with no obvious atmosphere, we appreciate air. After seeing planets orbiting extremely close to their stars, we appreciate the relatively calm orbit of Earth. After seeing rogue planets drifting alone, we appreciate the warmth of the sun. And after seeing how enormous the universe is, we appreciate how small our home really is. There is something humbling about that. Earth does not look powerful from space. It looks fragile. A thin blue layer surrounding a small sphere. A narrow atmospheric boundary separating the surface from the emptiness beyond. Everything we know is connected to that thin layer. Every ocean, every forest, every mountain, every city, every memory, every human story, every dream. All of it exists on one small planet. And yet that planet is capable of looking outward. That is perhaps one of the strangest things of all. The universe created stars. Stars created elements. Those elements formed planets. One planet developed oceans. Chemistry became more complex. Life appeared. And eventually, creatures living on that planet began looking back into space. They built telescopes. They measured starlight. They studied gravity. They discovered distant planets. And now those creatures can imagine traveling between worlds. That is what we have been doing tonight. Not physically, not with engines, but with imagination. And sometimes imagination is the first step toward understanding. Perhaps one day, humans will visit another planet. Maybe not one of the worlds we discussed tonight. Most are far too distant. But perhaps another world closer to home. Maybe Mars. Maybe one of the icy moons of the outer solar system. Maybe, far in the future, a planet around another star. The distances are enormous. The challenges are extraordinary. But every generation learns something that the previous generation did not know. A century ago, we had no confirmed planets around other stars. Today, we have discovered thousands. And the number will continue to grow. The catalog will become larger. The planets will become stranger. The measurements will become more precise. And eventually, perhaps, we will begin to understand not just what these worlds are like, but how common different types of planets really are. Maybe Earth-like worlds are common. Maybe they are rare. Maybe water worlds are everywhere. Maybe planets with thick atmospheres dominate the galaxy. Maybe most planets are nothing like anything we have imagined. We simply do not know yet. But we are looking, and that is enough. Because the universe is enormous. It does not reveal everything immediately. It offers clues. One faint signal at a time. One tiny shadow. One subtle gravitational wobble. One atmospheric fingerprint. One distant planet after another. And somewhere, tonight, another telescope may be collecting photons that have traveled across space for years. Those photons may have crossed the atmosphere of a planet we have never heard of. They may carry information about clouds, temperature, chemistry, perhaps an ocean, perhaps a world completely unlike anything we have seen. The light travels. It arrives. Someone analyzes it, and a new world becomes part of human knowledge. The process continues, quietly, patiently, across the darkness. So now, as we drift back toward Earth, allow the distant planets to become smaller. Let the hot worlds fade into the stars. Let the frozen worlds disappear into darkness. Let the giant planets become faint silhouettes. Let the worlds with two suns drift away. Let the rogue planets continue their lonely journeys. They do not need us. They will continue orbiting, turning, cooling, burning, evolving, long after this story ends. Long after our imaginary journey is finished, the planets will still be there. A hot Jupiter will continue racing around its star. A frozen world will continue drifting beneath its dim sun. A water-rich planet may continue carrying its hidden ocean. A rocky planet may continue turning beneath a red sky. A giant world may continue losing its atmosphere. A young planet may continue glowing with the heat of its formation. And somewhere in the darkness, an unknown planet will continue moving through a system we have never studied. The universe will continue. Stars will be born. Stars will die. Planets will form. Planets will collide. Atmospheres will change. Oceans will freeze. Ice will melt. Mountains will rise. Crust will crack. And time will keep moving. We cannot stop it. We cannot see all of it. But for a little while, we can imagine it. And perhaps that is enough. Because the night sky is no longer simply a collection of stars. Now, when you look upward, each point of light can carry a possibility. A planet may be there. Perhaps one. Perhaps several. Perhaps a world covered in clouds. Perhaps a frozen sphere. Perhaps a giant atmosphere. Perhaps a rocky planet. Perhaps something so strange that we have not yet invented a name for it. The stars are not empty. They are destinations for questions. And the darkness between them is not simply emptiness. It is space. Space where worlds move. Space where light travels. Space where planetary systems evolve. Space where the next discovery is already happening. So let the universe become quiet now. Let the stars remain far away. Let Earth turn gently beneath you. There is no need to travel any farther tonight. The planets can continue their journeys without us. You can simply rest. Somewhere beyond the window, the sky continues to turn. Somewhere far beyond the moon, planets continue orbiting their stars. Somewhere beyond our solar system, enormous oceans may be hidden beneath alien skies. Somewhere else, a planet may be passing through perpetual twilight. Somewhere else, metallic clouds may be forming. Somewhere else, a world may be freezing beneath a distant red sun. And somewhere very far away, perhaps a planet is turning beneath a sky where another intelligent being is looking upward and wondering the same thing we have wondered for so long. Are we alone? We do not know. Maybe one day we will. Until then, the planets remain. 100 strange worlds imagined in a single journey. 100 reminders of how creative nature can be. 100 distant possibilities scattered across the darkness. And beyond those 100, countless more. Unseen, unnamed, undiscovered, waiting. The universe is still enormous, still mysterious, still full of worlds. And you are here, on one small planet, beneath one ordinary star, resting safely as the night continues around you. The distant galaxies fade. The stars become softer. The planets disappear into the darkness. And the final thought can be very simple. We live on one world, in one planetary system, around one star, inside one galaxy, among an almost unimaginable number of others. And somehow, from this tiny world, we have learned to look outward. We have learned to wonder. We have learned to listen to the light. We have learned to find planets hidden in the darkness. And perhaps that is one of the most beautiful things about being here. Not that we know everything, but that we know there is so much more to discover. So let the unanswered questions remain above you tonight. Let them drift gently through the darkness. No need to solve them. No need to chase them. Just let them exist. Like distant stars. Like silent planets. Like worlds turning slowly beneath alien skies. The universe can keep its mysteries for another night. For now, the stars are quiet. The planets are distant. The darkness is calm. And Earth is turning gently beneath you. Slowly, silently, peacefully, as another night passes across our small blue world. And 100 strange planets continue their endless journeys. Somewhere, far beyond the darkness, under stars we may never see, on worlds we may never touch, the universe keeps turning. And for tonight, that is enough.